So good morning, everybody. Please try to find your seats. We want to get started.
Oh, I heard rumors that there are actually clubs. The other side. Maybe I have to.
Okay, good morning, everybody. My name is Inga Kamp. I'm working actually on the early phases of planet formation, more on the disk environment in which these planets are forming. I will be your host this morning, session chair. I'm going to introduce the speakers, but before doing that, there was some lost item found, a glove. So we have an owner. Good. Okay, it's an absolute pleasure for me to introduce a first speaker, which will give us an overview talk. It's Mariana Sanchez. She's basically on the move. She's now at Leiden Observatory, but she is moving in 2 weeks to the Max Planck Institute in Göttingen. And I think what she has been doing in the past years very successfully is integrating a lot of the processes of planet formation into n-body simulations, including, for example, also pebble accretion. And I think in that way, she created what I would call nice virtual observatories in which we can actually test the impact of all these processes on the outcome of planet formation and also the complex interplay of it. And I'm very much looking forward to Mariana telling us everything about building rocky worlds, how planetesimal compares to pebble accretion, and so on. Please take it away.
Hi, everyone. Can you hear me well? So good morning, and thank you for coming to the first talk of the day. And thank you very much for the organizers to invite me to give this talk. So I will focus mostly on the comparison between planetesimal and pebble accretion and how this is impacting the formation of rocky worlds and the delivery of volatiles. So to start, I will begin showing you again this well-known plot of planetary mass versus orbital period of all the confirmed planet population that we know, and where we can see 3 overdensities related to hot and cold Jupiters and the population of super Earths and sub-Neptunes. And here in the left corner, you can see our rocky worlds, and they have ranges in masses up to 5 10th masses and in radius up to 1.6 to Earth radius with a wide range of densities. And there is not just one number as upper limit because there is some overlapping here between the rocky worlds and the super Earth population. And to look into details about which surveys and instrumentations we can use actually to cover all this diagram, I think you can look to the keynote talk on Thursday. But to continue talking a little bit more about rocky planet composition, in this plot, you can see the range in mass that I showed you up to 10 Earth masses against the planetary radius. And it's overlapping here all the planet that has measured these 2 measurements and some density lines that are related with pure rock and Earth-like composition and water world. And you can see that somehow within 2 Earth masses, we can see just rocky planets. But if you increase the planetary mass, we are not only finding rocky planets, but water worlds and some Neptune-like planets. And these 2 populations are separated by the radius valley. You saw this plot a couple of times yesterday, but this radius is what actually separates the populations. And here I'm just showing you a few examples of the terrestrial planets in our own solar system and some other rocky worlds that we have both measurements with also the density for you to compare. So we can see there are many rocky planets within this 10 Earth masses range, providing that the radius is always below this radius valley. And there is some planets just close to the radius valley that they are between 2 and 5 Earth masses that could consider rocky worlds. And if you are between 5 and 10 Earth masses, you can find the sub-Neptune. So there is quite going on between this regime in masses. So let's see actually how and where we can form these rocky walls. So I'm showing you first one general picture of planet formation. So everything starts in a disk with gas and dust, and then the dust has a direct coagulation into millimeter, centimeter sized particles that we call paves, depending where they are within the planetary disk is its size. That in some places in the protoplanetary disk, we can have like overdensity of these particles due to accumulations. And through, for example, streaming instability, we can form planetesimals, these kilometer-sized particles. And up to here, the aerodynamic gas drag is really important to control the movement of these particles that we expect to move radially inwards through the star. Once the particles reach kilometer size, then is where the pebble accretion and or planetesimal accretion could take place into forming the protoplanets. And depending its core mass, it's that they can accrete a great amount of gas and become a gas giant, or a little bit of gas or not gas at all and become a terrestrial planet. And within the disk lifetime, then it's important to take into account the gravitational torque that the gas exerts onto the planet and take into account planetary migration when we are studying rocky planet and giant planet formation. But the start of the day is the comparison and planetesimal and versus pebble accretion, and where this is taking place within the protoplanetary disk is important for the volatility delivery and planetary composition. You will hear a bit more also in the keynote talk this afternoon. But this is completely linked with the snow lines and some important lines that are having a major role in this delivery of volatiles, that's the one that I'm showing here. And the location of these lines are related to the stellar mass. So I'm pointing here the location of these three lines. If we consider a sun-like star, but if we consider an M dwarf, this is changing like more or less an order of magnitude, and this will have an impact in rocky planet formation. So well, to continue talking about planetesimal and pebble accretion, I'm showing here an overview of the rest of the talk, in where I will start talking about classical theory, where we assume the planets were forming through planetesimal accretion, like a brief description of the mechanism, some words that tackle this rocky planet formation, then a little bit of where were the accretion challenges and the new observations that we have to change paradigm and start considering pebble accretion as a mechanism to form rocky planets, some works related to the rocky planet formation, some comparison between the two mechanisms, and end up with a challenge and future research directions. So let's start with planetesimal accretion. So here just a brief description of how this is working. So we have a planet, a protoplanet, an embryo kilometer particle that is growing by another kilometer-sized bodies, and is growing through direct collisions. So the accretion radius will be completely linked with the physical radius of the accreting body, and it's going to be enhanced by gravitational focusing. That will be related with the relative velocity between the bodies and the escape velocity. And due to this relationship between velocities, you can discriminate three different regimes of accretion. So first, all the particles are similar size, similar masses, and everything is growing like orderly. The velocities are comparable, and this is taking like really long time, up to sometimes 10 million years. After some collisions took place, then the larger bodies are gonna accrete faster. So we're gonna start in this regime. There's gonna be a runaway accretion, and the accretion rate will be linked to the mass of the accreting body. And this is happening a bit faster, maximum up to 1 million years. And it will end up in this oligarchic regime, in where the planet is accreting from all its feeding zone, and it's reaching more or less the mass of the moon and Mars, depending where they are in the disk. So there were many people who tried to understand planet formation through planetesimal accretion. I'm just showing here a couple of authors and teams. And I will just show you a couple of works about this. And most of them were based on M-body simulations and assuming always a giant planet in the system to track the terrestrial planet formation and water delivery. So here in this work, they use M-body simulations. They assume the disk was already evaporated from, the gas disk was already evaporated from the system. And they assumed there was going to be one Jupiter-like planet. They changed the location, the distance from the star and its eccentricity. And they tried to analyze mostly the impact on the eccentricity on the terrestrial planet formation. And you can see here in this eccentricity versus semi-major axis plot and different integration times how we can form terrestrial planets. And what they try to compare is starting from a Moon and Mars size embryo composition that grow by planetesimal accretion, actually the impact of the eccentricity. So assuming a Jupiter planet in a circular orbit, you can see how these rocky planets are not water rich, but let's say they could get like 10 to minus 2, 10 to minus 1 of water percentage in mass. But when you change in different simulations, when you change the eccentricity of the planet, this is decreasing. So if you increase the eccentricity of the planet, then you decrease the water available in the terrestrial planet population. So this is what they found. Moving forward to another work, also using M-body simulations, they tried to play a little bit with the initial distribution of embryos and trying to analyze the impact of the asteroid belt and the presence of two giant planets this time, Saturn and Jupiter-like planets, in the formation of terrestrial planets. Again, the same type of plot, eccentricity versus same major axis in different integration times. And what they found is that if they start from a Moon to Mars initial embryo distribution, this shallow embryo distribution is exciting the asteroid belt, but it's overproducing the mass of Mars. But if they use a more steeper distribution and a wider range in mass for the initial embryo distribution, at the end they can actually get a good Earth-Mars mass ratio, but they cannot get a dynamical hot asteroid belt. So this was one example of a work that is telling us that it's really important to include the migration and start everything from an early stage. And I'm showing you here one work that I lead at the beginning of my research, in where we also use M-body simulations. We again try to understand the impact of a giant planet, but not in terms of mass, not in terms of eccentricity or semi-major axis, but in terms of its mass. And we assume also a embryo distribution with sizes between Mars and clearly bigger and the Earth. But we play a little bit with the initial planetesimal distribution. And what we found is like actually giant planets can act as a dynamical barrier in the water delivery inside the terrestrial storm. So in here I'm showing you a plot of the percentage of planets that survive in the system against the giant planetary mass that we use. In terms of a planet that could survive in the habitable zone, planets that are completely dry or water wars. And you can see here like around 1.5 Jupiter mass, there is a declive in water wars and there is an enhancement in dry planet formation. So giant planets play an important role in water delivery of terrestrial planets. But moving forward to a recent series of papers based on this new generation planetary population synthesis model, where they not only include M-body interactions, but also include a gas-driven orbital migration, taking into account the disk evolution and both planetesimal and gas accretion. They tried to test again with this more complex model, the impact of two Jupiter-like planets in the formation and composition of terrestrial planets, the same type of plot here in different simulation time. And they tried to see the impact and compare what's happening if we include giant planets or what happens if we neglect them. And in terms of masses, that it's not a clear trend that you can see from the plots or actually any plot in the paper, but the main outcome is that they see that system with no giant planets, it seems to be well ordered in terms of orbital radius, in terms of masses, in terms of radius. And this is not always true when we compare with exoplanet sample, and potentially some long-term embodied simulations will be needed to explain that. But for sure, including migration was better mapping planetary composition. Okay, so there was a lot going on with planetesimal accretion, but there were some limitations, some challenges, especially in the formation of the close-in super-Earth population and the formation of giant planets, because it was quite challenging to form them before this dispersal. And in particular, there have been some challenging in trying to reproduce the water content of the terrestrial planets. So then, motivated by this, and new observations coming mostly from disk with a sensitivity of ALMA, we found out, doing a comparison of the dust budget in class 0, class 1, and class 2 disk with the exoplanet population, that planet formation really needs to happen early for us to have the dust material to form them. And if we see a sample of different protoplanetary disks from class 2 to debris disk, we can see how this mass in dust and pebbles is decreasing notably, several orders of magnitude during the time. So radial drift really needs to be efficient. So accounting for early planet migration and efficient radial drift is that this new pebble accretion theory took place, in where we are assuming that pebbles are drifting inwards throughout the star, and due to streaming instability at some within the disk, in some places, some planetesimals could form, and they will accrete efficient these millimeter, centimeter size particles, both inside, outside the snow line. And once the accreting body reach more or less the mass of Mars or Earth, this growing will be even more efficient. There's gonna be a runaway growth until it will stop when the accreting body reach the isolation mass, which will be related with the stellar mass and the Hayes scale of the disk. And this will be so efficient because it will have a different accretion radius. So when we are accounting for pebble accretion, the accretion radius will not just be related with the gravity of the planet, but also related with the gas drag. So the area of accretion will be enhanced when the particle is coming through the planet. If it's lost enough kinetic energy, then it will be captured by the planet. And this is making the accretion radius bigger and enhancing more collisions, and it's happening also faster. As you can see in this plot here, you can see the y-axis, the time scale of accretion across the disk. And for example, to form a planet of Turner's masses or a planetary core, it takes like 2 orders of magnitude less if we consider pebble accretion than if we consider planetesimal accretion, assuming at this lifetime of somewhere between 1 and 10 million years, it has a high impact. So pebble accretion could explain the rapid core formation within the disk. And that's why many people try to include this mechanism and try to study planet formation. And at the beginning, it was mostly focused on giant planet formation and super Earth, but with the time, it was also included to study rocky planet formation. And I will just try to go through some works that include them here. So in this work, no embodied simulations were taken into account, but as isolated embryos, different pebble fluxes were assumed with different initial dust masses, also including an evolving disk and orbital migration. And the aim was to understand the impact of changing the initial pebble flux, the initial dust reservoir. And they found that when changing the initial pebble flux, you can separate the formation path of Earth-like planets and the formation path of super Earth-like planets. In terms of water delivery in this pebble accretion mechanism, again, assuming isolated embryos, changing the gas accretion rate and the size of the gas disk, playing a little bit with these numbers that I forgot to mention before. The Stone numbers are related with the particle size of the pebble, and it will tell you how well it's coupled to the gas. So they play a little bit with this value and also the mass of the accreting body. And they found that Earth analogous could have a similar water fraction if the delivery is coming from icy pebbles. And then more related to the volatile deliveries in this work, it has been already, the first one was 2021, and it's still becoming a bit more complex. It's focusing on the delivery not just of water, but also molecules based on carbon and nitrogen. And they can actually match the volatile content of the terrestrial planet in our solar system with this pebble model. So pebble accretion, it can solve some of our previous issues. And close to the end of the talk, I would like to spend some minutes talking about this model that is part of a work that I lead, and I started during my PhD and become more robust during my postdoc here at Leiden University. And our model includes embodied simulations with external effects. So we also include the disk evolution, the orbital migration, and until then just considering Taiwan migration, so exclusively for rocky planets, also star-planet tidal interactions, because we are focusing on stars that are M dwarfs. We start again from a moon-size embryo distribution, but the different thing that we account for are that everything is happening in really compact dust disk, and this was motivated by recent high sensitivity ALMA observations around M dwarfs and K dwarfs, in where we can find really compact disk, some of them like within 20 AU, some of them really, really compact within 5 AU. So we are assuming that the pebble reservoir is coming from a 20 AU disk that, due to really efficient radial drift, is shrink to a 2 AU disk, in where we are going to place our embryos, and we are going to study if we can actually form a rocky planet and super Earth-like planet really close into the star. So our formation scenarios are shown here. We start assuming a 0.1 solar mass star, and we play a little bit with some initial conditions. So at the beginning, we place the embryos just beyond the snow line. Later on, we account for embryos both inside and outside the snow line, assuming always a low viscosity. And then we decided, okay, we will increase the viscosity 1 order of magnitude, play a little bit with pebble flux. And then these 3 scenarios were just accounting pebble accretion, and we wanted to compare what's happening now if we include planetesimal accretion instead of pebble accretion. And then we focus on more massive M dwarfs, 0.3 and 0.5, and our aim was just to compare pebble and planetesimal accretion in a disk with low viscosity. So the first main result that I can show you is based on a 0.1 solar star. And you can see in this planetary mass versus semi-major axis plot some of the confirmed exoplanet population in black, in single system or as a part of multiplanetary system, with this diverse set of simulations. And what we found is that in the cases in where we assume efficient radial drift in a disk with a low viscosity and planets growing by pebble accretion, is where we can actually reproduce the super Earth population around M dwarfs. What's going on? Sorry. But if we account for planetesimal accretion, we are able also to reproduce some of the super Earth population, but also we are able to reproduce Earth-like and sub-Earth-like planets. But if instead we account for pebble accretion, but we use high disk viscosity and a low pebble flux. We cannot reproduce even Earth-like planets. We just form sub-Earth-like planets. So the initial pebble flux, the viscosity of the disk, and the accretion mechanism is having a high impact in the resulting population. And moving to the more massive end dwarfs, we can see the same effect, that when we assume a efficient radial drift and a disk with low viscosity, we can actually reproduce pretty well the planetary mass and the semi-major axis distribution of the observed exoplanets. So in here, I'm showing you like solid dots, all the confirmed exoplanets, and open dots are our simulations. And we can see here these 3 dashed lines that are representing the isolation mass, the pebble isolation mass. And I just overplot here those lines to show you how important are planet-planet collisions after the planet reached the isolation mass. So the isolation mass is not the only parameter that is setting and shaping the final planetary masses, but the later collisions play also an important role. What we did later was trying to compare this planetary radius versus planetary mass, the densities of our planets, if they were actually matching the observations. And what we found is these 2 mechanisms that it was also studied before has a really high impact in the water delivery. So if we account just for planetesimals, we reach these like 2 extremes populations, either just dry planets or water worlds. But if we include the pebble accretion mechanism, we get a gradient, and we actually can reproduce some water deliveries with small fractions more similar to what we know today. And to wrap up, I wanted to show you two more works. This work was made by one master's student at Leiden Observatory, and she used exactly the same model that I presented you earlier, but instead of assuming a fixed inner edge of the disk, she assumed an evolved inner edge of the disk using 2 different prescriptions, using accounting for the fact that the inner edge of the disk is set as the magnetospheric cavity, so it's going to move outwards during the contraction time of the star, and then accounting for the inner radius as the rotation radius. So in that case, while the star is spinning up, it will move inwards. And we found that where and how the disk inner edge of the disk is evolving, it will have an impact in the formation of ultra-short period planets, some potential lava worlds. And also this will be favored for fast rotating stars with weak magnetic fields. So in here, I'm showing you the planetary mass versus orbital period of all our simulations and some of the observed exoplanets in single system and with companions. And yes, it's promising to link the formation of ultra-short period planets around stars with these particular conditions. And to finish, I would like to show something in preparation, which is related to the model that I was presenting before, but now accounting for gas accretion or just pebble accretion onto the planet, again, focus on M dwarf as a host star. And what we found when we include gas accretion, this is preliminary, still we are working on that, but we found that some planets can have not atmosphere at all, or up to 15% of gas in mass. And I was just wondering, motivated by the talks that I listened yesterday about atmospheres, if this will have an impact actually in future detections, atmosphere detections, because if the planet initially has really high percentage of gas in mass, if they could actually retain some atmosphere, or how it can influence, for example, the cosmic shoreline that they were talking yesterday. So I think it will be interesting to see if you would like to discuss it further. So yeah, there were many things that pebble accretion could solve, but it's not all roses. So The thing about pebble accretion, it can be so efficient, but it requires sustained pebble flux, and this will be related, completely linked with the disk structure, the viscosity of the disk, and the scale height. And pebble isolation mass is not all that we need to consider, because the later mechanism of accretion will play an important role. And then to end up, still there are some uncertainties in volatile retention under this mechanism as well. So I will end with this list of conclusion and future research directions, perhaps. So we know that planetary accretion is slow and collision limited, so it may take up to million years to form. If we include pebble accretion, then it's enabled rapid core accretion, and it can solve some issues related to fast core growth. And efficient pebble accretion could explain why the exoplanet population that we see is not much in the class 2 disk, but early disk, so everything may happen early. But these two mechanisms somehow are complementary because they need to work together. Because even though pebble accretion is dominated like an early core growth, then planetesimal accretion is needed to take into account for a late stage of collision and also through the dynamical evolution of the planetary system. And which mechanism we will use, it has a direct impact on the water delivery and other volatiles that we need a bit further study, especially in these M-body simulations studies that we are not considered so far. So thank you very much for your attention.
Thank you for a very clear, whoops, I'm hanging, for a very clear overview talk and also for finishing well in time. So we have plenty of time for questions. I'm just looking first in the back. So I see a question all the way in the back. Waving. And if the people who are sitting here could squeeze in a little bit, because there are people arriving late and they have a hard time getting a seat just because you're not compressed enough. So please move. Okay. This is a bit like pebble accretion towards the inner part. I lost track of where the microphone moved, but there was a question. Yes.
Okay, hello, Bennett Skinner, McMaster University. I was pretty surprised at how significant an amount of gas, like hydrogen and helium, you could get onto a sub-Earth mass planet. I would guess, like, even before any like type of mass loss was accounted for, that it would be going out just in hydrostatic equilibrium to a very significant fraction of the Hill sphere. So I'm just asking, are these just around like just barely sub-Earth mass planets, or did you find that my intuition there is not reflecting what you see in your findings?
So I guess you're referring to this. Let's go there. Wrong direction. So you're referring why these Earth-like planets or super Earth get this high amount of gas, right?
Yes, specifically the sub.
Okay, so this is actually because we start gas accretion once the planet reaches the isolation mass. And around a really low Rho mass star, like 0.1 solar mass, the isolation mass could be like 0.5 Earth masses. So if you start accretion that early, and this planet is living like in a disk with a 10 million years lifetime, then is why you can get that high percentage of mass.
Okay, more questions? I see one in the middle there.
Yeah, thank you. So,
Can you first state your name, please?
oh, I'm sorry, Hannah Diamondalo, Space Telescope. Towards the beginning of the talk, you mentioned several different ice lines. And here it looks like it's mostly just rock and water. I'm wondering if you could talk more about that.
Yeah, that is what we are aiming for to include later on.
Oh.
Because I'm just naming them. I mean, the silicate line we are considering for our inner edge of the disk. Then we are mostly including the water line when we are assuming the composition. At the beginning was just rock and water, and now it's just rock and water and hydrogen. But the idea would be just to get the model more complex and include more volatiles. So this all of the snow line makes sense, and try to understand a broader delivery, right, of volatiles.
Thank you.
So there's a question down here.
Hi, I'm Melissa McClure, Leiden Observatory. So thank you for a really great talk. I was just wondering, my understanding from meteoritics studies in the solar system is that it's still very much a controversy whether Earth could have formed by pebble accretion or by planetesimal accretion. You have one group saying that at most 4% of Earth could have formed by pebble accretion, and the other group saying it's like 40%. But in the models that you have, it looks like you're mostly focused on M stars. Have
Yeah.
you tried something at like a solar mass star?
No, but it's what we are aiming for. So the next step will be try to use this model to expand it to different stellar masses and particularly to solar mass star to try to understand like formation of the Earth and the water delivery. But it will be most likely try to use the two accretion mechanism, both planetesimal and pebble accretion, to try to constrain better. That will be the next step. Yeah.
Okay.
More questions? Oh, there's one who has already a microphone.
Madeline Broom, UC Santa Cruz. You mentioned the giant planets are effective dynamical barriers for delivering water to the terrestrials. Can we then use the density of observed terrestrials to infer like a historical or current presence of a giant planet?
Can you tell me again the last part?
Can we use the density of the observed terrestrials, like inferring their composition,
Yeah.
to infer the presence of a historical giant planet or a current one?
Yeah, that will be interesting. It's not that straightforward, but because most of the models, except for this new generation of models, they were more basic in terms of composition. So it was taking the giant planet mostly linked with its mass, you know? It was not trying to link a density of a giant planet with. In most of the work, what it has been done is it was assumed that under some conditions a giant planet was formed, and in a preliminary stage using an analytical model, and the giant planet has like 1-2 grams centimeters cube density. But then when you put that in the M-body code, then it kind of lose the previous history, right? So you are making some simplifications in giant planet. So it's mostly related to its mass or its location or the eccentricity or inclination of its orbits.
So I'm going to follow up on the question.
Can you first state your name?
Sure. You know me.
I know you.
Another Hawaii. So I'm going to follow up on the question from the front. There are works that demonstrate pebble accretion is formation of terrestrial planets with pebble accretion is inconsistent with our understanding of isotopic property of Earth. Any comment on that?
Yeah, that's actually I can say a little bit about the life program, and this will be like a next step, right? Is we will try to use M-body simulations. We will try to take into account all the physics that we took before that I couldn't go into detail, but if some of you is interested, we can talk later. And the next step will be trying to include some astrochemistry and try to see how we can merge the two worlds. So try to account for all the physics and gravitational interactions with some some more complex astrochemistry, so we can better map the Earth's composition.
More questions? There's one here in the front.
Hi, Tad Kamasic, Oxford. So it was really interesting that you needed low disk viscosity to explain super Earth formation. And this seems to go in a similar direction as other recent work, like by Eugene Chang, that says we don't even need any disk viscosity to explain planetary systems. And so my basic question is, what happened to the MRI? Do we even need disk viscosity? And what does that imply about planet formation and disk evolution?
Yeah, okay. So what we are using here is a viscosity model. So we are assuming that in the inner disk, the disk is evolving by viscosity, and in the outer disk is evolving by the stellar irradiation, right? So we need to see how everything changes if we include the other mechanism. But we have been playing a little bit with the viscosity that is actually taking place when you calculate the planet-disk interactions and the pave accretion, and then what happened to the viscosity that you use to actually get your gas density profile. So it seems to be like two of them are important. So we found that if you use like an alpha parameter of 10 to minus 4 or less, this is enhancing the radial drift and the planetary growth. But also it has a major role, the viscosity you assume for your density profile. So if you have a really, really dense inner disk, this is playing also an important part of this efficient growth.
Are there more questions? We still have some time. Are there any online questions? No? There's a question over there.
Thank you for a really nice talk, Helen Williams from Cambridge. So you mentioned towards the end of the talk that your models of pebble accretion could potentially say something about planetary magnetic fields, and I was wondering if you could elaborate a bit more on that.
Yeah, well, the model of pebble accretion itself is not accounting for the magnetic field, but how we model the innervation of the disk. Because we are not accounting for star-planet magnetic interaction. That's the thing. That's I guess what you were wondering. So we just account in one of the scenarios that the innervation of the disk was moving with the magnetospheric radius. So we assume that the magnetic field conservation, so this 10 million years, and we use the magnetic field evolution and the contraction of the star to get to this outward evolution of the innervation of the disk. But we just account for the star-planet tidal interaction. But we did some research, and the thing is, this star-planet magnetic interaction will actually take place later on in the dynamical evolution of the system. So within 50, 100 million years, which is our simulation time, the tidal interactions will play a major role. But then in a giga-year time scale, the magnetic interaction will take like a major role. It's not much, but it can change like between up to 10–20% of the final location of the star. So our next step in that direction will be later on to include the magnetic interactions with the planet. Yeah.
So if there are no other questions, I may have a last question actually, which is way more down to Earth, to the ground. You know, these simulations take a long time. They're computationally very expensive. And yet you say we want to incorporate astrochemistry, you know, maybe more isotope information to compare with the solar system. How do you see this happen? Do you think this is computationally feasible, or do we need to look also into new methods, how to do this and how to speed it up?
Yeah. I mean, looking into new methods will always be like a good thing, because we need to, I have not much knowledge myself, but including machine learning and the AI in all of this will have like a major impact, I believe, in the integration time. But it has been like, it has been an improvement, right, in this last, especially in the last decade, in terms of different type of embodied code that can be parallelized and decrease integration time quite a lot. Like if, it can be like reduced like 1/3 of the time, like before. So I guess it just, it should be like a compensation, no?
Just make the existing codes faster.
Yes, exactly.
Okay. Well, then, if there are any other questions, we have Discord, so feel free to keep asking questions to the speakers also on Discord. And with that, I would like to thank Mariana Sanchez one more time. Thank you. And we are going to move to the next presentation, which is a contributed talk by Ida Bemar. Oh, there's the other glove. Who picks up the first one? That's the second one, just in case. Now you're complete again. No more freezing. I think so. Maybe we have some shoes or something. I mean, just. Okay, so while we are setting up, so the next presentation is by Ida Bemart from the Flatiron Institute in the US, and she will talk about the link between host star chemistry and planet density.
There we go. Okay. Oh, thank you. This is to advance. I can just like press this, right? Okay. Hi, everyone. Can people hear me okay? Cool. Yeah, I'm excited to be here. And today I'm going to be talking about a link that we've uncovered between the densities of rocky planets and the chemistry of their host stars that we think is connected to galactic scale effects potentially. So, in the field of exoplanets, we have this saying that goes, know thy star, know thy planet, which basically means that in order to understand planets and their formation pathways, we really need a good handle on the properties of their host stars. So properties like, for example, chemical abundances. So, we discovered that stars that are rich in heavy elemental abundances, like, for elements like iron, these stars tend to host planets that are both larger and closer in terms of their orbital period. And that's the planet metallicity correlation, which was super great evidence for the core accretion model of planet formation. But even more detailed chemical abundances in host stars can tell us even more about planets, like even what they might be made of. So for example, you can imagine that if you have detailed chemical abundances for a star, like for many different elements, and that star hosts a rocky planet, if you can measure good values for the planet's mass and radius, you can begin to constrain its bulk density. Then when you tie that bulk density to the detailed chemical abundances of the host star, which kind of characterize the initial chemical composition of that planet forming material, you can actually begin to start probing the interior chemical composition of the planet, like even, what minerals it's made of. So if we want to tie exoplanet compositions to the compositions of their host stars, it's much easier to focus on planets that are rocky. So, planets on this side of the radius valley. And that's because it just makes it more straightforward to compare the rocky component in planets to the rocky elemental abundances of their host stars. We don't have to worry about planetary atmospheres complicating things. So to do these studies, in general, we want to construct these samples of rocky planets where they're very well characterized. So they have really good masses and radii, and they also hopefully have host stars where the host stars have accurate and homogeneous chemical abundances for many elements. But that's a lot of criteria to meet, right? And so a lot of these studies really suffer from small sample sizes. So we wanted to do a sort of updated version of this study, and to address the issue of collecting enough homogeneous and accurate stellar abundances for different chemical elements, we turned to the current phase of the Sloan Digital Sky Survey. So this is SDSS-5, and it's basically taking spectra and using that spectra to infer chemical abundances for 5 million stars across the entire sky. And within SDSS-5, we're using the Milky Way Mapper survey, which is providing us with near-infrared spectra at very high resolution to infer chemical abundances. So the SDSS-5 chemical abundance pipeline makes use of stellar atmosphere models, which are very accurate in the solar-like or sun-like regimes, like this part of the HR diagram. But they really begin to struggle when we want to use them to infer the chemical abundances of M dwarfs. And that's because M dwarfs are cool enough to host molecules in their atmospheres that kind of create these complex forests of molecular lines. You can kind of see this in this plot here on the right, where we have a bunch of synthetic stellar spectra going down in temperature from top to bottom. And the bottom spectrum corresponds to an M dwarf. And you can see that, comparatively, it looks a lot more complex because of the presence of these molecular lines that we don't understand well in terms of like their opacities, their line strengths. So it's very hard to model them. And so it's very hard to characterize M dwarf chemistry with these methods. And that's too bad because M dwarfs are super important for rocky planets, as we've heard many times throughout this conference. Because M dwarfs are, first of all, the most common type of star in the solar neighborhood, but they're also the best stars for both detecting and characterizing rocky planets because of their small masses and sizes that enhance these like transit and RV signatures. So we thought it was very important to find a way to measure chemical abundances for M dwarfs in this study. So what we did is we turned to a data-driven approach, which basically allows us to infer chemical abundances for M dwarfs given just their spectra. We don't rely on stellar atmosphere models at all. So the way that we constructed this data-driven model for M dwarf abundances is we used this training set that we drew from SDSS-5 that was basically composed of binary systems where one of the stars is an M dwarf and the other is an FGK dwarf or a solar-like star. And then because the two stars are gravitationally bound, we can assume that they formed from the same parent molecular cloud and were thus born from the same material and are chemically homogeneous. And then the SDSS-5 abundance pipeline provides reliable abundances for the FGK dwarfs. So we just tagged those to the M dwarf companions, and those M dwarfs form the basis of our training set. So our final binary training set is illustrated here, where we have the two stars plotted in Gmag versus temperature space, and they're colored by the iron abundances of the solar-like companion from the SDSS-5 pipeline. So that basically allowed us to infer pretty detailed chemical abundances, so abundances for a wide set of elements for a bunch of M dwarfs in SDSS-5. And some of those M dwarfs are rocky planet hosts. So then we were able to construct the sample of rocky planets that included 22 planets where we have 18 around solar-like stars and 4 around M dwarfs. And I'm plotting the stars that host these rocky planets in this plot here in a certain type of chemical abundance parameter space of magnesium over iron versus iron. And this particular chemical space is really good at delineating out different structures in the Milky Way, so namely the thin and thick galactic disk. So that clump you see kind of near the top, that's the thick disk, and the clump near the bottom is the thin disk. And so you can see that most of the rocky planet systems in our sample are thin disk inhabitants, but we do have a few thick disk members, which will be interesting later on for the final results of this study. But first, I just want to explain why this ratio of magnesium over iron is so good at tracing out different structures in the Milky Way. So it's because magnesium is a prominent alpha process element, and the ratio of alpha elements to iron really characterizes the galactic chemical evolution of the Milky Way. So basically, in the early times of our galaxy, the chemical enrichment landscape was very dominated by core collapse supernovae, which produced both iron peak and alpha elements. And so that kind of characterizes the thick disk and the halo of the Milky Way, which are these older structures that formed in earlier times. And then over time, the chemical enrichment landscape began to be dominated by products from type 1a supernova instead, which are just iron peak elements. So that kind of characterizes the more recent or the younger components of the Milky Way, like the thin disk. And so because of that, you get that difference in magnesium over iron in these different Milky Way structures. And that's really interesting because when we tried to see if there were any strong correlations between rocky planet properties that probe their interiors and different chemical abundances of the host stars, we found that there's this pretty strong correlation between planet density and magnesium over iron, which I'm showing here. And you can see that I'm actually labeling some of the thick disk planets in our sample. So we have TOI 561b, which we've heard a bit about. It's a pretty confident thick disk member, as well as Kepler 10b, which is kind of at that thin thick disk transition zone. So this relation kind of makes sense if you assume that rocky planets have roughly Earth-like interior structures. So I'm talking like, an iron-dominated core and a silicate-dominated mantle. And then you can imagine that if you have a rocky planet that forms in iron poor regions, like the Milky Way's thick disk, you have less iron to contribute to the core. And so you have a smaller core and you have an overall lower density, which is kind of what we see. And we also think that this correlation may even be tied to rocky planet atmospheres. And that's because there are results from molecular dynamics simulations that show that when you have less iron in your planet's interior, you are not as good at holding on to volatile species within the planet. So if you have a rocky planet that's heated up to a very high temperature and it becomes a lava world, it's going to potentially be better at outgassing to form a secondary atmosphere if it's forming in a region with less iron, like the thick disk. And there is some evidence now that this may be true. So we recently heard from Joanna Teskey yesterday about their work on the planet TOI 561b and how using JWST observations, they were able to show that it likely hosts a thick volatile atmosphere. And TOI 561b is also in our sample. It's that confident thick disk member. So this is kind of forming this comprehensive picture of how rocky planets may vary in terms of their compositions in the thin versus thick disk, where maybe in the thick disk, they are more likely to host secondary atmospheres because of the low iron content in general. So this is a very intriguing scenario, but I think it's pretty speculative so far. So I think we really need larger samples of rocky planets to see if it holds, especially rocky planets in the thick disk of our Milky Way. But I think it's still very indicative of exciting directions that exoplanets is going in, placing planet demographics in the galactic context. So I'm very excited to see what comes next, and that's all I have. Thank you.
Thanks for staying perfect on time. We have time for questions. I see in the back questions. Maybe we first go there.
Hey, nice talk. I'm Chris Worth from the University of Chicago. So in the paper for this result on the left, you test 15 different potential trends. And not just MGFE, like SIFE and SI over H, for example. Can you talk about potential look elsewhere penalties from doing that as part of the research and how that might affect your results?
Sorry, potential what?
Look elsewhere penalties, like the fact that you're testing 20 different potential trends and you find something significant in one of them.
You mean just comment on why maybe I don't see a similar trend in other elemental abundances?
Yes, and just how much that would reduce the statistical significance of the results, since you're looking at 20 different things and finding something with a 1 in 20 chance in one of the 20 different things.
Yeah, I got you. So magnesium is not the only alpha process element. So if we are hoping to see this correlation that characterizes rocky planet compositions in the thin versus thick disk, we might expect to also see it in other alpha elements like silicon, calcium, etc. So I did test those and they don't have as strong of a correlation. It's a bit weaker. And so that's a little bit troubling, but at the same time, it also potentially makes sense because magnesium is actually the purest alpha element. It's the one that's only produced in core collapse supernova. Whereas a type 1a supernova, I think is actually sometimes produces a little bit of silicon, a little bit of calcium. So it kind of makes sense that we would see it strongest in this ratio.
Okay, thank you. So there was another question over there.
Hi, Drew Weisserman, McMaster University. In your sample, looks like most of your stars are FGK stars, and you only have 4 M dwarfs that don't seem to span a huge range of MG over FE. Are you able to comment in any way on how this trend might change across the different spectral types you're looking at, or is that something you need a larger sample size to probe?
Yeah, sure. So if we consider just the FGK dwarfs, the correlation statistic is so p-value is 0.001, you can see it on this plot. And when you add the 4 M dwarfs, it gets a bit more significant to 0.0005. But yeah, we definitely need more M dwarf hosted rocky planets for.
Okay, I think maybe if it's a very quick question. Okay, well, that would be the very last question, and all the rest, please ask your questions on Discord. There's more time to interact with the speakers there. Or in the coffee break.
Hey, thanks for the talk. So, in Gianna's talk yesterday, she also mentioned that this TOI 561 star is enriched in C and O, as well as being poor in iron. I wonder at what point you can not assume anymore that the rocky part of the planet is made in the magnesium silicates and like the carbon and oxygen content start to play a role in the building blocks.
Yeah, definitely. So, I think it's definitely possible that because TOI 561b likely does have this volatile rich atmosphere, that is making the overall density lower, which is a big reason why it's kind of like anchoring this trend.
Yeah, exactly. So I'm wondering if the density of the building blocks could also change.
What do you mean by the density of the building
Like the
blocks?
bulk density of what you're in here, you'd be assuming that the mantle is MgSiO3 or something, right? But at what point is that not really a good assumption?
You mean like, is there still some like?
Yeah, like does the
cluster-
carbon and oxygen content start to play a role in the chemistry?
Right. I don't know. That's a really interesting question. I honestly have no idea. I'd love to talk to modeling experts about that.
Okay, I'm afraid we have to close here, so let's thank Ida again for the talk. And we move to the next contributed talk, and while we are setting up, let me introduce the speaker. So it's Haiyang Wang from Beijing in China. It is. And he will talk about hybrid accretion and how it leaves an imprint on the volatile depletion of planets.
So here's me from Beijing, China, and also University of Copenhagen. Okay, let's do that. So giving the first 2 talks this morning, we will continue to talk about how can we actually leverage the very important star-planet chemical connection, in particular volatile depletion, to infer the formation pathways of rocky planets. Here is the volatile depletion schematic plot, which shows basically moderator volatiles compared to refractories are actually quite reduced in the rocky planet relative to their host star. And this is also an area where Robert Spagering and Paulo Sossi and also Tim Lichtenberg, among others, have been very active working on. As summarized in the review talk, the planetesimal accretion and pebble accretion are 2 leading theories, among others, that for rocky planet formation, even not for planet formation in general. So I will not go into details here again, but I would emphasize that planetesimal accretion and pebble accretion are not mutually exclusive. Rather, they operate with very relative importance at different amplitudes and different conditions. So, giving a theory, if that would work, regardless of the specific formation, it will imprint their signature in the final outcome of the form of the planet, in the particular case, like chemical composition. So here is a comparison of the composition for a few rock-forming lithophiles that are across a few solar system rocky bodies and also exoplanet rocky material as inferred from the measurement of planet engulfment events and by measuring their co-moving stellar pairs and also planetary pollution onto weather dwarf atmospheres. So even though the variation of this volatile depletion remains large, but we can arguably assume that by putting all of this together, the volatile depletion, also called devolatilization, is potential universal feature in rocky planets relative to their host stars. So the important question to ask is that can we leverage this potential universal feature to infer the formation pathways of rocky planets? So one of the leading efforts towards this direction is the stochastic accretion model, which parameterizes the formation pathway to the simple logistic closed function with two key variables. One is T naught that represents a mean mid-plane temperature, and sigma indicates the width of the fitting zone for an intervallic object, as shown here for the cases of Earth and Vesta. In comparison, Vesta, the curve looks a little bit narrower, which suggests that the Vesta might have accreted material in a relatively confined region. Well, in comparison, for Earth or Earth-like planets, it has a more smooth out pattern, which is actually interpreted to have accreted material across the wider region of the disk. So I like this model for its simplicity and also elegance, and also can help us to parameter the formation pathways. So actually, I also like to take in the Vesta model as a baseline for my further exploration of volatile depleted planetesimals, while being agnostic of their exact formation patterns. But this work also comes with a caveat, which builds on the premise that pebbles are not, or if they are not empowered in volatiles, then certainly pebble accretion alone won't be able to explain the composition of volatile depletion of the Earth. If this premise could be relaxed, then of course the conclusion will also warrant re-investigation. Indeed, in the recent studies, the pebbles has been shown that has been able to be thermally processed while they are destiny through the envelope that has been contracted onto the central Green body. So this is just like meters passing through an atmosphere. They was just sublimated and lost into the space. So given the same principle and theory, we can do further explore what material, or in terms of individual elements, going to be sublimated out of these pebbles where they're being accreted. So to do so, we need to calculate the individual sublimation temperature for this individual element against the pressure and temperature of the envelope environment. So with that, then the game is more become like to see which side is going to win between the planetary environmental temperature and the individual sublimation temperature, to help us to trace which element and at which point they are going to be sublimated, or otherwise they will be returned. So this will cause the intrinsic self-fractionation between the elements per pebble. And if the material has been sublimated, we also need to care about their fate, if they will be out of the system or they will recycle back. So to understand that, our colleague Ziyan Xu, who is also close for this work, ran this 3D hydrodynamic simulation, which actually nicely shown that once the sublimated material has gone about 2 boundary radii, it will actually meet with the disk flow that's penetrated to that regime, and then physically take out this sublimated material. And this has demonstrated to be a very efficient process, as shown with the panel A at the beginning and to D, just in time scale of years, not many years, and this material, over 97% of 99, going to be lost out of the system. So this is a theory. If a theory would work, it needs to explain the best data we have. Here we test against our best target we know in terms of the Mars and Earth for their composition. And to start with Mars, here we placed both planetesimal accretion and also pebble accretion. And into this framework, we have done not only in the fault process, but also with the Bayesian inference framework, and to see which component or otherwise their mixture going to be able to explain the data to the highest Bayesian evidence. So the best model we found is reveals actually there will be about a quarter contribution from pebble accretion, while the dominant 3/4 will come from planetesimal accretion. And this is purely on the elemental level, and it's also actually found it's consistent with the independent isotopic studies, in this case like silicon isotopes, which indeed shows that Mars resembles closer to Vesta, right, to the Earth. So here we assume the planetesimal animation to be Vesta-like. This not necessary to be the case, and certainly may not be the case. So we also phrase the assumption by varying both T naught and sigma to representing the average property of a population of potential planetesimals that have been accreted onto the planet. So with that, actually, we redo this analysis with the Bayesian inferences And the results we found actually don't change our conclusion. That is, the formation of Mars is dominated by planetesimal accretion. It's super clear. And for now, let's move on to Earth, which is a slightly complicated case. The reason is because also based on a lot of other evidence, including geological records, that giant impact is probably responsible for the formation of the moon. So I'll take that as granted and place it as a third potential in the member component into the interplay together with the pebble growing proto-Earth and also with the impactor together with the population of planetesimals, and also analyze them within the Bayesian inference framework, and to see which contribution would be able to explain the best data. So the best model that we found actually reveals that up to 15% of the contribution would come from planetesimals, but the remaining that would actually require pebble accretion to grow body to proto-Earth and the impactor. So, and we also, of course, we have to vary the assumption and phrase that regarding planetesimals and to representing different populations, and the results also don't change our conclusion. That is, the formation of Earth is dominated by pebble accretion. So here's a very brief summary of all the models that we have exploited with the Bayesian framework inferences, and the overall results lead us to conclude that volatile tabulation is a chemical fingerprint of hybrid accretion of rocky planet, while the contributions from planetesimals and pebbles are in contrast for Earth and Mars. So we also envisage that the hybrid accretion pathway, as it's studied here, together with the developed Bayesian inference framework, would potentially have broad implications for helping us to interpret the compositional diversity of rocky exoplanets. Yeah, I will stop here. Thank you. And I'd love to take any questions.
Thank you very much. Very interesting talk, especially in the context of what was discussed earlier. I'm sure there are plenty of questions. Let's go first to the middle up there.
Okay, so I'm Adriana, I'm from UC Davis. So if Mars is dominated by planetesimal accretion and Earth is dominated by pebbles, where does the pebble flux come from that is not recorded in Mars? Because there should not be enough mass of pebbles generated between Earth and Mars that it can explain that difference.
Very, very good question. And this may be simply due to the scenario where Mars is getting closer to the gas giant, and this actually may play some trap role actually to stop that material. And Mars actually could be actually formed even actually later than Earth. So that's still something very interesting to explore, but there's some alternative actually to explain that. Mars, indeed, it's a particular case why it's growing to be such a smaller scenario.
Okay, there's another question up there. Maybe you can give the microphone to the back. Yes, thank you.
Hi, thank you. Xander Byrne, University of Cambridge. How, with regards to the Earth volatile depletion model, where you include the effective impacts, how well do we understand the volatile depletion profile as a result of impacts? How is that model kind of parameterized?
Yeah, very good question. Actually, the best model we have for the volatile depletion remains to be Earth. It's very Earth-centric. It's been studied for decades. It's very calibrated. But for anything else, including Mars, that remains a large uncertainty. But on Mars, we have now inside mission actually to trace that relatively less depleted for Earth. So that's actually the best scenario we have for the solar system. Of course, you have asteroids, as shown earlier. So they have large variation of volatile depletion. So most important, except for exoplanets in our context. So there's the kind of like weather dwarf measurements. That is the first order information that we can really know about exoplanet composition. And plus now that also with the planet engulfment, there's also very high precision measurements because we require it to locate the companion stars to be relevant essentially. So that's actually for some specific targets, the precision level achieved can really help to be able to be place a very robust constraint to recover this potential formation pathways. The large variation I showed earlier is just represent the range of potential exoplanet material, not a specific target.
Thank you.
Okay, do we have a very last quick question, Rob? Well, make it quick.
Hi, Rob Spargaren, kapitein Instituut in Groningen. Thank you for a great talk. My question is, for the Earth, you predict that 64% of the Earth is basically depleted by the pebble accretion pathway. But on your pebble ablation slide, where you show the depletion of elements as a function of, through ablation in the atmosphere as a function of planetary mass, you show that most elements are fully ablated for planet masses above 0.5 Earth masses, I believe. So can rocky planets even grow larger than 0.5 Earth masses through pebble accretion? And then how do you get to a fraction of 0.64 for the Earth?
This is a very, very critical question. Thank you for mentioning that, but I didn't have time actually to explain. So here, there's a very important layer, which is called the inner radiative layer, just above the magma ocean and beneath that envelope. That was built up because of the SiO evaporation in there. So that increased the pressure in there, then caused this radiative layer. So actually that layer played a critical role to stop anything more reflected than silicon going to be actually preserved. So that can keep growing the planet once even you beyond 0.5 or 6 something. Yeah.
Well, I think we need to close here. I saw many more questions. Please use Discord to exchange the questions and get answers from the speaker. So let's thank Ayang Wang again. Thank you. And now we move to the last speaker of the session, which is Oya Saveri. And she will actually talk about how to make Mercury planets, so something we haven't touched upon yet. Please take it away.
Hello. Hello. Hello.
Keep using your phone.
Am I audible? Hello. Yeah, better. Yeah, great. So yeah, hello, and 10 minutes to coffee break, so I think we're doing okay. Right, so I'm going to talk a bit about forming Mercury-like planets, which is something we have in our own backyard, of course, Mercury itself, but we've also, amongst the big population of exoplanets, seen many more Mercury-like planets. So that's basically planets with core mass fraction more than 50 to 60%, which is essentially that it has a huge core and a much thinner mantle on top of it. And in general, there's been two possible theories proposed, also for Mercury, but also for these other planets that we find around other stars. That one of them is mantle stripping, which is essentially that there was a giant collision or run and impact collision that stripped away the mantle of the planet and left the core behind. And hence, we have a larger core to mass fraction. And the other is an in situ formation method, which is the classical condensation method, where we have a solar or a protoplanetary nebular disk in which we just condense solids and the planetesimal, and it somehow the iron fragments are separated from the silicate minerals, and we get a larger iron mass fraction in these planets. So I think we'll explore more of the latter scenario today. And before we move to that, I would just try to start a bit closer from home. So thankfully to the talks before, I don't have to work too hard to explain this, but essentially we use the composition of the star as a proxy to the composition of the planets. This is generally done in the field to break the mass radius degeneracy that we commonly observe. This is also plot from Hayang Wang's paper from 2019. And the yellow line you see is the composition of the sun measured from the solar photosphere. And the blue is that of Earth as we calculate from mantle peridotites. Essentially, and it's a plot of the TC50, which is the temperature at which 50% of the element has condensed in the solar nebula versus the abundances. Now so the TC50 is calculated according to the nebular condensation at a fixed pressure and composition using Gibbs free energy minimization. And the composition here is what we measured as, for example, for the sun from the solar photosphere. And for the other disks, we see it from stellar surveys such as Gala or other surveys, Hypatia, Apogee, etc. But that's the thing. The TC50 condensation temperature would change as a function of the composition of the star. So this stellar composition relation that we see, that the MgSI, Fe, the refractory elements have a one-to-one correlation with that of the sun, and the trend is decreasing with TC50 in abundance for the more volatile elements. It doesn't necessarily need to look like this, even if devolatilization is common among other planets and other stellar nebulas. So yeah, the one-to-one relation might not hold true for other systems. One of the major ratio in the stellar composition space that causes a huge difference is known to be the C2O ratio, simply because the carbon monoxide gas is a very stable gas in the stellar stellar space. And all the oxygen that would be present in the system would then be sequestered with the carbon. And hence, the more the carbon in the system, the more oxygen will be taken away. Of course, you would expect the C2O ratio to be 1, where the major change happens. But there's also metals such as other magnesium, iron, etc. in the gaseous form, which are competing for the oxygen. And hence, this is a very old paper from Larimer Bartholomew from 1979. And what you see is essentially that the iron condensation temperature stays the same because it's not dependent on the C2O ratio. It condenses directly from the iron gas state to the iron solid state. But the other elements such as aluminum, magnesium, iron all take a dip, magnesium, silicon all take a dip at around 0.8, significantly down. So essentially, in comparison to iron, we're decreasing the condensation temperature of all the other major rock forming elements. And this could be crucial space to just enrich something in iron in the inner regions of the disk. So just going on this further, we wanted to explore how the C2O ratio, so specifically the stars which have a global C2O ratio higher than 0.8 would react in such a situation, and what would be the solids that would be condensing in these disks, and how would they change the condensation temperature in a bit more detail. So we tried to do this in a more robust manner. We took a data set from Hobbs Goto telescope of FGK dwarfs, and we varied the C2O between 0.65 to 0.95. We take this elemental space of most of the major elements, and we run nebular condensation sequences. So you go from a high temperature to low temperature, and at each temperature step, you do Gibbs free energy minimization to see what are the solids that are condensing in your disk. We do this from 1800 to 400 Kelvin at a disk pressure of 10 raised to -4 bars. We've also varied the disk pressure, but I'm not mentioning those results here, but feel free to discuss with me afterwards if you want to know more. Another thing that we really try to input in this model is we try to use solid solutions to see how that would change the condensation temperature, as has been from the canonical condensation sequences for the solar nebula beforehand. And also we try to include more reducing species such as iron silicides, which haven't been considered before, but could be very stable in these high CO environments, which are more reducing in nature, while they're not stable in the solar nebula. So going on to the results, this is the more canonical case that's in hand with the other previous studies that have been done. We see a lot of condensation of oxides at the upper regions of the disk around 1800 to 1400 Kelvin. After that, the iron starts condensing, and then also simultaneously the magnesium and silicon. So hence the iron and magnesium silicon condensation is quite close. We see other two sequences as well. In transitional sequences, we see more of iron silicides condensing and silicon carbide, as well as a huge peak of graphite that you see. And similarly, in reducing sequences, which we call above CO of 0.91, we see a huge peak of, at very high temperatures already, of carbon, silicon carbide, FeSi, and Fe3Si. So we see a lot of these reducing species. And this is all to say essentially that when we go to more reducing sequences, the disk temperatures change the condensation temperatures quite a bit. So titanium becomes more refractory, silicon, aluminum less, and sulfur, sodium a lot more. So essentially, we shouldn't use these disk temperatures, 50% condensation temperature, as material properties of the disk, but we need to modulate them as per the composition of the star. Going very quickly already, actually, Hayang explained this quite well. We used the core stochastic accretion model to just model how this would impact the composition of the planetesimals. So we use a central feeding temperature at around 1050 Kelvin and a feeding zone of 225, Gaussian feeding zone, to see how this compositional change in the disk changes the composition of the planets. And what we see, the first case above is that of Sun, and the one below is the most extreme case that we had of CO 0.95. And what you see is that in solar like this, the Fe to O to Si ratios stay pretty much constant through the disk. But in the other bottom case, at higher temperatures in the disk, you see a lot more iron forming, and those get at lower temperatures, you form more sun-like sequences. So there's a huge variation in Fe to O ratios, and in the inner regions, you can really enrich the planetesimals with iron and carbon-rich bulk compositions. Just a very quick sneak peek into the other project that we're doing. That is essentially, we use the composition that we formed from the models in the previous experiment as the starting composition for high pressure temperature experiments. And what we see essentially is we form a lot of these reduced assemblages of FES melt and MgFES solid, as well as these melt which are very sulfur rich, which are quite different from what we would expect in a solar nebular planetesimal or Earth-like composition planetesimals, which are where the sulfur is always going more towards the core. So with that, I will leave the conclusion slide on and take some questions. Sorry if I was a bit late.
Yes. Thank you very much. I'm sure there are plenty of questions as usual. Let's look for somebody who hasn't asked a question yet. Well. Well, okay, we go for another.
I appreciate all the complexities that goes into your work. My question is, how do you suggest to form a Mercury-like planet with all these properties?
Sorry, can you repeat that?
How do you suggest to form a Mercury-like planet, a planet similar to Mercury with all these complications?
Without these complications.
All of these.
Oh, I mean.
Yes, all these complications included.
Right, thank you. Yes, thank you. So if you just have a star, which would be very high in carbon to oxygen ratio, you would very easily form Mercury-like planets at higher regions in the disk. So the one that's sort of in this region, that's essentially very Mercury-like because you have a high Fe to O ratio, very low MgSi ratio, as well as an enrichment in volatiles such as carbon and sulfur. So,
yeah, okay. We have time for one more question. Well, here's one.
Hi, Roja. This is Kaustubh Hakim from Leuven in Brussels. My question is about the transitional region. So what makes this transitional region interesting for you? Is it like you assume some kind of sequential equilibrium condensation, like one of the Jake Moriarty 2014 papers, or do you simply assume equilibrium condensation, but still find this transition region?
Yeah, thank you. That's a great question. We do not consider sequential condensation. We're just doing equilibrium, assuming equilibrium. So what we also notice, the transitional sequences are interesting because they're sort of intermediary in nature between solar type sequences where you still get a lot of oxygen-rich oxygen-rich condensates at higher temperature, but then in the middle region of the disk, more reduced species take over. The idea is that it's not only the carbon to oxygen ratio that plays a role, but there's also an interplay of the metallicity of the star. So if you have higher metallicity, it kind of it takes up a little more oxygen, and then these condensates, the reduced condensates can accrete even quicker. So for a high metallicity, I can get reduced condensate at a lower C2O ratio, even if not for the low metallicity case.
Okay, thank you. I am afraid in the view of time, we need to move on. So let's thank all the speakers, especially also. Okay. So we are moving now into the flash talks before the coffee break, and I will hand over to Tim.
All right, before we all go for coffee, please stay around once to give our amazing poster presenters a chance to present their work. Yeah, so one before? Yes. If you're on this list, please come to the left side and prepare for your poster flash talk. And you have 1 minute for each of those flash talks, and then you will get a big fat stop sign. So please adhere to the time. And yeah, let's go. Oh, stop, before we go, actually. True. So please don't forget about the poster competition. The deadline is on Friday in the morning, so that our posters get the attention they need. Okay, could we try to calm down a bit so that we give the poster flash talks some space? Thank you. Let's go.
All right. Hi, everyone. So my name is Lorenzo Cesario. I'm a master's student here at the University of Groningen. And my poster is on the characterization of the oxidation state of rocky planets. So LIFE, the Large Interferometer for Exoplanet, is a really cool European-based space mission for a formation-flying space-based nulling interferometer. And the oxidation state, I don't think really needs an introduction considering what we're here for, but as you know, it greatly affects the volatiles that are outcast in the secondary atmospheres of rocky planets. So in our project, essentially we study to what extent such a future mission will be able to tell us about the underlying geochemical environment of these planets, so not just the detection of singular biosignatures. So if you're interested in the results, which highlight the potential of such a future mission to tell us more about these prebiotic and abiotic environments on rocky exoplanets, feel free to come to my poster. It's right outside on the left. Thank you.
Hi, I'm Melissa Hobson from Geneva Observatory, and I'm presenting the results of the Espresso Consortium's follow-up of small transiting planets. So one of our main goals was to probe the rocky to gaseous transition for planets with insolations between 50 and 200 times the insolation of the Earth. Here you can see those planets on a mass radius diagram, and we have a tentative mass threshold at 6 Earth masses, roughly, between rocky and volatile planets, although this is rather small number statistics. If you want to know what happens in higher and lower insolation regimes, come check out the poster. Can I get the next slide? Another thing we looked at was comparing some of the planetary masses in each system to the typical protoplanetary disk masses in a similar stellar mass range, because the planets forming the disk, they shouldn't be more massive than the entirety of the mass on the disk. And we find that the sum of the planet masses is always very similar to the median class 2 disk masses, suggesting that the planets either form super efficiently, form earlier, or form preferentially massive disks. I also have on the poster an overview of the whole survey, how the planet masses link to stellar metallicity, and how our observance strategy impacts the results.
So
On the long-term evolution of rocky worlds, volatile exchange between the interior and the exterior could be important. It's definitely important on Earth. So some people have looked into how much stagnant lid rocky worlds can outgas, and the conclusions have been different. One study suggests that planets larger than about 4 to 5 Earth masses can't outgas at all. Another study says that all sizes outgas, but they stop after a few billion years. So I've been running some models and find another conclusion. So basically that all sizes can outgas and that they don't stop, but the previous trend that larger ones tend to outgas less proportionally still holds. Now, is there a second slide? Yeah, and this is an example of the models we run. So, and another aspect is that these planets tend to become compositionally stratified in their interiors, particularly the larger ones and the lower viscosity ones.
Hi everyone, I'm Shaggy from Duisburg-Essen University in Germany. We are modeling hydrodynamic and thermodynamic properties of magma board gas atmosphere interfaces. So we are using Pluto code to model the experiment which is running in ETH Zurich by Paolo Sossi and Elodie Defoe. She is also here and has a poster as well. We are interested to understand the flow morphology of the heated sphere for different geometries, different Reynolds number, and different boundary conditions. So for more information, come to our posters.
So, hello, I'm Dennis Wehner, also from the University of Duisburg-Essen. And my poster is about a new technique to do grid-based simulations of protoplanetary disk with forming planets inside. And the new thing here is that we run the disk and the planet on separate grids, which allows to resolve the planet, you can see on the right-hand side really well, while still taking into account planet-disk interactions. And then we can simulate the whole system with the planet and simulate, for example, the atmosphere of a planet or circumplanetary disks. If you want to take a closer look, my poster is near the entrance to this room. Thank you.
Hello, my name is Tina. I'm here as a representative of the Biogeodynamic Network. It has a similar vision as Rocky World, so we try to combine different disciplines and expertise, so from earth science to exoplanets. And here you see like the systems we are looking at. So we start from geodynamics, which concerns the interior people. We look at climate, so for all people who like atmospheres, and the remaining Earth scientists. We also look into biological evolution and why this might be interesting for your research. You can I don't know what I did.
All right, so we've previously described how rotation in the case of the Earth can unify observed CMB pressures with comparatively lower pressures of core formation inferred from moderately acidophile element abundances. What we haven't previously talked about is how rotation systematically affects the interiors of rocky worlds. And what we found is that internal pressures in rotating bodies can be lowered to less than 40% that of a corresponding non-rotating planet, with rotating planets becoming significantly extended in the equatorial plane, such that cross-sections can grow by a factor of 3. And you may think that these are extreme end cases, but both SPH and N-body simulations demonstrate that rapid rotation is the expected outcome of the giant impact stage of planet formation. And as a result, studies of planet formation need to account for rotation at every step in the process. And so to address that, I present scaling laws for angular momentum and pressure relationships in rotating terrestrial planets. All right, thank you.
Thank you.
Hi, thank you very much. So my name's Helen. So over the last 10 years or so, we've learned that magma ocean processes are fairly generic on many rocky bodies. What we don't understand is how they define their internal structure or indeed control. Oop, thank you. Or control physical interactions between different reservoirs, silicate, metal, solid, liquid on those planets. This is something we've tried to address using studies of ancient 3.6 billion-year-old rocks from Earth. If you're interested in talking about that with me, then my poster is over there, so you can just get yourself a coffee. And if you want to chat about that, or indeed any other planetary bodies, I'd be really keen to chat to you. Thank you.
Okay. Well, good morning, everyone. Good morning. I'm Carmen Jauques for Centro de Astrobiología in Spain, in Madrid. And I have a question, and it's, how would you expect if there were more rocky worlds than, how would you feel if there were more rocky worlds than we expect? Because maybe we are missing an entire hidden population of exotrojans or orbital bodies, but in this case with planetary sizes. But their complex motion around the Lagrange point, combined with the noisy data, makes it extremely difficult to detect their transits. But instead of focusing on a static signal, we propose to follow the river. It means to track the Trojan motion around the Lagrange point through all the data. So indeed, with this approach, we identify a total of 28 Trojan candidates in the Kepler data. But for more details and results, I invite you to visit and to vote my poster. Thank you.
All right, good morning, everyone. I'm Afonso, and I'm doing a PhD in astronomy, but actually my background is in biology, and a lot of my biology colleagues think I'm insane for coming into astronomy. But in any case, that allows me to study astrobiology from a different perspective. So I study habitability by looking at the extremes of life on Earth from a biological perspective, but incorporating knowledge of extreme environments here into other planets, using lab data we have to produce models and statistical analysis of life on Earth, and then try to predict where life may be able to survive on other worlds in the solar system and beyond. My poster is right in the line where we'll be waiting for coffee, so just look to your right and you'll find me, and we can talk about life on other planets. Thank you.
Hi everyone, I'm Gergely from the Uni of Edinburgh. I also work in astrobiology. Essentially, I do a parameter exploration, or as I like to call it, a scientific word building, and I'm making new levels for Super Mario. We know that Earth is a rocky planet and life has emerged here. So I want to see how the physical environment of different rocky planets that are possible affect the chemistry, especially with the focus of the small molecule that I labeled as Super Mario hydrogen cyanide that will then be transported to the surface via Raynaud processes where it can form the building blocks of life. And then I do these simulations on different environments and see whether we can do this. So if you want to talk about rain, life, or Super Mario, come and see me at poster 68, I think, by the coffee.
Hi, everybody. My name is Noisy Salts, and thank you for the opportunity to present my light zucker work. Spoiler alert, host star properties is predictive of planetary radii. When we look beyond the planet and stellar metallicity correlation, we found some really interesting connections between the host stars and its planets. So we used GALA-DR4, which provide us up to 32 elemental abundances per host stars, which we have 104 of them. So when we group the elements based on the condensation temperature, we found some really interesting results. We can see that host stars of small exoplanets are enriched in rock-forming elements relative to iron, relative to large host stars of large exoplanets, and vice versa for CNO to hydrogen. Here's a QR code for our upcoming article if you're interested in the statistics, in the analysis, which are, in my unbiased opinion, are very cool. And we also invite you to our breakout session on Thursday.
So we are at Rocky Worlds Conference, and we are really interested in knowing about interiors. But what if I were to tell you the best type of planets to understand about the chemistry of interiors are not rocky worlds, but sub-Neptunes, and especially sub-Neptunes below equilibrium temperatures of 1000 Kelvin. So that's my pitch. Come find me at poster 88.
Hi. I'm Lynn. I'm working on the moon, and the moon was formed by a giant impact between the proto-Earth and Mars-sized object, which results in the moon in a magma ocean stage. And this lunar magma ocean crystallized with olivine pyroxene settled at the bottom to form the lunar cumulate, and the anorthite crystal floats to form the lunar crusts. And I'm interested about the dynamics of the lunar cumulate surrounding by a magma ocean to see if thermal instability can develop before the end of the magma ocean solidification and what is the preferred mode of convection. And I use the phase change boundary condition between the magma ocean and the lunar cumulates. And with linear stability analysis and direct numerical simulation, we obtain several timescales like the duration for degree 1 thermal overturn. And very quickly, there is also the poster of Catherine Dotz, a postdoc of my team, working on the formation of the lunar crusts from slushy magma ocean. So thanks.
Last one.
Hi, my name is Alex McGinty. I'm a second year PhD student at the University of Oxford working with Per Ambot. And for the last couple of months, I've been working on trying to understand the phase curve of TOI 561b by modeling it in the GCM ISCA. And what we've basically found is by assuming that there's no sort of reflection or albedo in the GCM, it's too hot across the entire planet compared to the NOS1 phase curve. So if you want to learn more about this phase curve, come into my poster, it's right by where you get coffee. I've got comparisons to both NOS1 and NOS2 in the GCM.
Awesome. Thank you so much. Thank you all for the presenters. Now we have coffee break. You're released, and we will start again at 11:30. Thank you.
You need to say something?
Yeah.
All right, everyone, please take your seats. I'm sitting in the, yeah. Okay, let's start. So hello, everyone. Great. Hello, everyone. So we will continue with the second part of this morning. I'm Shamila Miguel. I will be the chair. And the first great talk that we will have is by Francesca Miozzi from ETH Zurich. She will be telling us everything about interactions between magma oceans and atmospheres in the lab. Whoa, no pressure. In 10 minutes, by the way.
Yeah, exactly. Well, thank you, Jamila, for the introduction. Thank you to the organizing committee for giving me the chance of presenting this work here. I'm currently a Marie Curie Fellow at ETH Zurich, but these results were obtained when I was at Carnegie Science. So I don't need to convince you all that working on interaction of atmosphere with magma ocean is important. But if I want to give you a perspective of how I see things, these are the questions I'm trying to answer. So in the years, there has been different authors that have been trying to question what happens when you have a primary atmosphere interacting with like a molten layer, which can be the first phase of planetary accretion or can be like sub-Neptunes in their more evolved stage. But the key point is like we can have two main processes going on. One is ingassing, and when I speak about ingassing, I speak about volatile phases dissolving in a melt, so entering the structure of melts. And this is fundamental to keep in mind that is a pressure and temperature dependent effect. So if our surface is a different pressure and temperature as in sub-Neptunes, or if we're going in depth in the magma ocean column, the amount of volatiles we can store in the magma is going to change. And how do we know how much it changed? With experiments. But then the other reaction that can happen, I generalized it here, is oxides plus H2 that gives a metallic phase plus H2O. This is really fundamental when you're speaking about iron. So it would be FeO plus H2 that gives Fe plus H2O. And then the question is like, what's the fate of this water? How does it stay in the melt if it stays in the melt? And does it stay in the melt or is it present as a free fluid phase? So liquid water in the melt. So this is fundamental because the chemistry of the magma controls its properties in depth, and the physical properties of the melt controls all the large-scale property of a planet that determine how these evolve. So that's what we set off doing because there are no experiments essentially on the solubility in depth of H2 into a magma ocean. We wanted to study what happens when you equilibrate a FeO-bearing pyrolite, so a sort of like representative of an early mantle of a differentiated planet, with H2 at high pressure and temperature to have a sense of what's going on in the magma column. So we did diamond anvil cell experiments. The idea is that we compress a little platelet of a sample in between two diamonds. This is the pressure range in which we worked. And the idea is that because diamonds are transparent to radiation, then we can use two very powerful lasers to reach the temperatures we need to melt these samples. Because the key component here is that the melting temperature of primordial composition are so high that it's almost impossible to attain them in a lab setting with something that is not lasers. But these sort of like create other complications that we're going to see later. We wanted then to quantify if we have solubility of hydrogen in the melt, and the only way one of the ways we can do it is by using nanosims. The idea with nanosims is that we work on recovered samples, so samples outside the diamond anvil cell. We bombard them with primary ions, which induce a sort of like cascade effect, and secondary ions and small molecules are ejected from the sample and get collected by a magnet, separate by mass charge ratio, and quantified. Key point of our work is that we measured OH minuses. So we measured the mass of OH minus, but for how the instrument is calibrated, what we see is water equivalent. So my results are going to be shown as water, but we don't actually have access to the speciation of this water in the melt. It can be H2, it can be OH minuses, we don't know. But we know how much hydrogen there is. So I said we work on recovered samples. So the idea is that once you do the experiment, you have to recover this little tiny disk, and somewhere is here, there's the sample where you have to cut a slice. This seems kind of like big, but I'm saying tiny because this is the size of one of your hair in the same scale. So this is actually kind of tiny. Then we use an instrument that allows us to slice this said sample up to a certain thickness that is not thick enough and like not thin enough to blast our sample, and there's sufficient space to guarantee the possibility of doing this nanosims analysis. Now, that's what we see moving on to the results when we started getting into the sample. So these are pictures that were taken while milling the sample with the experiment. So here you see this big hole was excavated, and this is my sample. The striking thing is that all of these have this big central sort of dark patch that is a resin-filled void. So this is filled with resin, that is what I used to recover the experiment, but before that it was empty. So it means that there was a phase that we were not able to recover after opening the diamond anvil cell. The other striking things here is that we see these sort of like metallic balls that are in between the cavity and this portion that is the melt. And these can be identified as iron-enriched blebs. So we started with FeO-bearing pyrolite. So we started with no metallic iron at all. So the fact that we're seeing metallic iron here is telling us that already one process happened. So we reduce the FeO component from the interaction with H2, and we form metallic iron that stays at the boundary of this cavity. Then we made some like in-depth analysis of these metal phases. And you can see there's a change in the shape and texture from these 4 samples. This is one of the higher pressure sample. And the other thing is that we have all these bubbles inside. And typically, these bubbles are light element exolution due to temperature quench. So when we are at the experimental condition, the melt and the bond between atoms are vibrating a lot, so they can host a lot of volatile phases inside. But once you cut the experimental temperature, it's like you're freezing the bonds in place. And so all the volatiles that previously were hosted inside the melt are forced to quickly leave it. So this is the analog of what you would see like on a volcanic breccia, for example, or volcanic rocks on Earth. So you have all these bubbles that indicates that volatiles were there. These are the result of the chemistry. So we use the chemical mapping, in particular the calcium mapping, to identify the melt portion, because it's fairly evident from like here that there's a melt enrichment. So this was useful because then when we were looking at the sample, we could see that in the molten portion, so the portion where there was like an enrichment in calcium, we also had some small bubbles. I'm not sure if you can see it from afar, but there are like a lot of like small difference in the grain size here. They are well visible. So also in this case, also in the silicate melt portion of the sample, we have this volatile exolution due to temperature quench. Now, these are the nanosims analysis. This is an example. So this is the field of view you're looking at here. And the brighter the pixel, the more present is the element we're looking at. So here we have hydrogen and silicon. And this is the portion of the melt delimited by these 2 guides for the eyes. You can see that we have a like very high hydrogen enrichment. And instead, you can perceive like a small depletion of silicon. So we are seeing here, we have less silicon in the melt as seen in the chemistry before, and a lot of hydrogen. So these are the result of all the samples as pressure over water content. And mind, I said water because this is what we measure. So in all the samples, we see an average of like 6 weight% water equivalent. That translates to like 0.7 weight% if we were thinking about this water as molecular H2. So this is a lot. This is like way more than what expected so far. And then we have like 0.8 weight% in the crystallized phases in equilibrium with the melt. Be mindful that because I just mentioned we have bubbles in the melt that likely had volatiles inside that were lost upon opening the cell, this is a lower boundary. So this number is likely much higher at the experimental conditions, so at high pressure and high temperature. But this is what we see on the recovered experiment after releasing temperature and pressure. So there's another observation that we can make, and is that the lower pressure sample are like kind of well consolidated. There are very little fracture, and there's this big giant cavity in the middle. While the highest pressure sample, we have this sort of like iron-rich portion that is very fragmented and intercalated with the silicate, and the cavity is not well visible. It's kind of like all messed up. So this is an indication actually of the fact that in the low pressure experiment, we had 3 miscible phases stable at the experimental conditions. So the iron-rich bleb, the silicate, and the fluid that was populating this void. And because we know that we reduced the iron oxygen component by interaction with H2, this likely was that water. So the water produced by the reduction of the iron cannot enter the silicate and stays out. While when we are at high pressure and temperature, we enter the domain of 1 miscible phase, so everything is together, and then it separates when we remove the temperature. So these mean that in this range, we encounter the pyrrolite plus H2 solvus, so the boundary above which everything is 1 single phase. So what does it mean for our planets? It means that when we're interacting a magma ocean with an atmosphere, there are likely 2 processes going on. One is dissolution of H2. We don't know in which form, if H2 or H minuses or what, but we know that the melt is being saturated. In the meanwhile, we are also reacting the FeO component with hydrogen to produce this water plus iron. But because the melt has already been saturated by hydrogen in this condition, most of this water likely is out as a free fluid phase, so it doesn't get in the structure. So this means that atmosphere magma ocean interaction can really produce like sensitive amount of water. And so if we now look at it in the planetary scale, this means that this water can have a different fate depending on temperature and the dynamic style of the magma ocean. So if everything is well entrained, then it can be carried in depth. But if we have like a slowly convective magma ocean, then this water can likely outgas from the surface layer and leave behind a mantle with a stratification with an FeO poor layer here that is rich in hydrogen that sort of like act as a lid for the bottom part. Then there is the mysterious scenario in which we have three miscible phase, so my brain cannot fathom what would happen in this case. So this is all. These are the conclusions I just recapped, but I want to leave with this nice image of the sample and welcome any questions.
Okay, questions? See one up there.
Thanks for the great talk. I wanted to ask about the last diagram. How would you start to the last slide? Sorry, go back to the last slide with the 3 different scenarios. Like, what do you think we need to do to figure out which one is relevant for a certain planet?
I mean, probably run computation with free water in there, because so far everyone has looked at like particles of water in trains or bubbles, but bubbles of like hydrogen. So I think like looking at like liquid water entrained in a magma convective can be a good start, but I wouldn't know how to do that. Like, that's what I would hope to see.
There is one question here.
Thank you so much, Francesca.
Remember to say your name.
Charles-Edouard Boucaré, York University in Canada. I have a question about the pressure at which you move from 2 phases, or at least when the water is present in a single phase, from this transition where now water is fully in the silicate phase. In your recent paper, you mentioned the pressure of about 45 GPa.
Yeah.
But the number that I had in mind from the low pressure petrology literature is more a few GPAs.
Yeah, that's all a matter of temperature in reality, because this is like, we think we see the transition when we have this sample that is sort of like midway into the 2 regime. But here we're working at like 4,700 Kelvin. So normally in petrology, the miscibility zone is seen at like 6 GPa or like 7 GPa, but because you're working like 1,000 Kelvin, so there's a correlation with temperature. So we don't know how this boundary goes because we only have 1 point, but it might go like this way in a temperature pressure regime or vertically. We would need a mapping of the PT space to actually see how it goes when you go down, because it's correlated with temperature.
Thank you so much.
Okay, let's thank our speaker again. And the next talk is by James Roger from University of Cambridge. He will be telling us about hydrogen silicate miscibility and the consequences for structure and evolution of subneptunes.
Great. Thank you very much. So yeah, the last talk was a great introduction to what I'm going to talk about today, which is also about miscibility. But let's take a step back and let's look at the mass-radius relation that we've seen a couple of times so far this week. So I'm going to be talking about subneptunes. And so these are these planets up here, right? These are the ones that are larger, typically larger mass, typically larger radius. They're counterparts of the super-Earths, which are smaller mass, typically smaller masses, and they're also more irradiated. And I want us to think about 2 empirical things we can really gather confidently from this diagram. So the first sounds really, really obvious. We're at the Rocky Worlds conference, is that rock is possible in our galaxy. The galaxy can build rock. It sounds really simple, but it's an argument that I'm going to use to build a subneptune. The other empirical thing that we can learn is that for the very largest subneptunes, the ones that are approaching the size of Neptune itself, the only way to build a planet that is that large for a given mass is with a significant amount of hydrogen. There's just no other compositional component in the element in the periodic table that you can use to build such a puffy planet. And so if we want to build the simplest sub-Neptune model and try and understand it, what we know empirically is that silicate rock and hydrogen are in our galaxy and they're in planets. And so we want to understand the simplest model, which is a hydrogen-dominated envelope on top of a silicate-dominated interior. And let's rewind a little bit in terms of our approaches to this. So if we go back to just over 10 years ago, maybe a little bit more than just over 10 years ago, we would have seen models that look like this. So what we have is a magma ocean, a convecting magma ocean, and on top of that is a hydrogen-dominated envelope. And these models were really crucial for actually predicting things like the radius valley, and they've helped us understand lots of the demographics that we see in the small exoplanet population. The next sort of regime or paradigm shift that then included in these models was to note that those original models predicted very high temperatures at the bases of these envelopes. So when a sub-Neptune is young, maybe only a few million years old, you can get temperatures that are nearly 10,000 Kelvin at the base of this envelope. And so what that means is that you are going to do a lot of chemistry. You have a very reducing envelope, you have a very oxidizing interior, and so you're going to produce things like water and carbon-bearing species, silicon-bearing species, etc. And the conclusion from both of these models, and we've seen some of these models so far this week, in terms of evolution, and this is really what I want to drive as the focus of this talk, is what does the evolution really say? Is that we have a cooling hydrogen-dominated envelope that contracts with time as it radiates into space, and the size of our silicate-dominated interior remains roughly the same size. There's a little tiny bit of contraction maybe, but it's approximately the same size. And this is true for whether you do or you don't include chemistry. However, and actually the last talk was a really nice introduction to this, when we look at the state of matter in hydrogen silicate, we're seeing some interesting things. So these are density functional theory molecular dynamic simulations. So essentially what you do is you take a bunch of hydrogen atoms, you take a bunch of silicate atoms, and you put them at a temperature and a pressure that we think is relevant for the base of the interior of a sub-Neptune. And you let quantum mechanics go, and what you end up with, once it's found its steady state, is that hydrogen gas and silicate melt are miscible. So miscibility is slightly different to solubility. When we're dissolving a gas into a liquid, think CO2 dissolving into our ocean, you can saturate the liquid. Miscibility is different. It means you can mix your two chemical components in any proportion you want. So think I could make a 10% vodka, which is a miscible mixture of ethanol and water, or I could make a 90% proof vodka. So that's what miscibility is. And the implications of that are quite profound when you actually model it in a self-consistent way in the interior of a sub-Neptune. So what we can do is we can construct the phase diagram, which we heard in the last talk, of the mixture of silicate and hydrogen. So we're used to a phase diagram for a single species like water as a function of temperature and pressure, and you see your different phases. This is a phase diagram for the mixture of two components. So I have actually pressure coming through the board, but on the x-axis now I have hydrogen mole fraction and temperature. And this binodal surface, which is also sometimes called a solvus, is really, really important. So if I'm at temperatures below the binodal surface, then my two chemical components are immiscible. So I'm going to have separate liquid magma rain, essentially, and I'm going to have vapor species, so vaporized rock and hydrogen. As I move deeper into my planet, the temperature is going to rise, and I'm now going to sit above this binodal, and I'm now going to be, everything's going to be miscible. My silicate and my hydrogen are going to mix perfectly. And so what we did is we've built an interior structure model, and we've looked at the implications for the structure and the evolution of these planets. So we're moving from a picture that looks like this to a picture that looks a bit more like this. So that binodal surface, which essentially represents a phase change between of hydrogen and silicate, is now a really convenient definition for the line that separates the miscible interior and the immiscible envelope. So the binodal surface sits here, and everything beneath it is a supercritical miscible mixture of hydrogen and silicate. Above that, we have phase separation. We essentially have silicate rain with a little bit of hydrogen dissolved inside. We have silicate vapor, and we have hydrogen gas. And these things are immiscible. We get the separate phases. And we get a bit of rain out, and this changes some of the heat transport at the base of the envelope, and then eventually move up to a more distilled envelope. And when we then look at the evolution, this changes quite significantly. So we move from something that looks like this to something that looks like this. So this binodal surface radially contracts inwards through the planet. And so, and instead of having those kind of 10,000 Kelvin interfaces, we now only have 4,000 Kelvin, and that's because it's defined by where the binodal is in the phase diagram. And as the planet cools and contracts, what happens is the binodal also cools and contracts. And an analogy I like to think about is that this is a phase change front moving through the planet. So this is a phase change front moving through a bottle of distilled water. And in the same way, a phase change front moves through the sub-Neptune as it cools and contracts. This analogy breaks down immediately, right? Because this is just pure water and only one chemical component. This is the phase change between a mixture of two components. And so when we then look at evolution curves of sub-Neptunes when we include miscibility, whereas this is planet radius as a function of time, a standard sub-Neptune with no miscibility taken into account has this very rapid contraction with time. But a miscible model, because we are storing a lot of hydrogen now in our miscible interior, contracts far slower. And that's because we're redistributing the silica as this binodal surface moves radially through the planet. And we think that this is probably the best way of testing whether miscibility is or isn't happening in the population, because we're predicting much slower contraction of young sub-Neptunes. And so if we can go and measure and detect a load of sub-Neptunes, we think this is the way to do it. And this is where some of our ongoing work is, how can we actually use the demographics of exoplanets to test this theory? This plot here is just showing the fraction of total hydrogen mass of the planet that's stored in that miscible interior. So in the standard model, we have no miscibility. There is no hydrogen stored in the interior. So of course, we have 0% of our hydrogen stored in the interior. But in the miscible model, we start with 75% of our total hydrogen mass that was stored in the interior. And then as the planet evolves, it releases that hydrogen as that binodal surface moves through the planet. Now, before I come to my conclusions, I want to advertise two separate things. The first is a completely separate paper that's going to go on the archive tomorrow, which is actually looking at sub-Neptunes again, but looking at how you can use atmospheric escape to constrain the properties, the interior composition of sub-Neptunes. And one of the potentially more spicy things we got to do in the paper is use the observation of escaping hydrogen from K218b. And from that, you can rule out the Heyschen scenario at about 4 sigma level. If you would like to understand what it means to tentatively rule out something at the 4 sigma level, please read the paper or come and talk to me. Very happy to chat about that. And if you also want to know whether we consider kicking Ethan off the paper because he's not called James, you can also come and ask me that. And then the final thing I want to advertise is a breakout session on Thursday that myself and Greg Cook are hosting. We're going to talk about sub-Neptunes and water content and all these sorts of things. So please come along if you'd like to hear about that. And with that, I will just conclude to say that hydrogen and silica are miscible at around 4,000 Kelvin. And this dramatically changes the interior composition and the structure of these sub-Neptunes. We need to understand how this will present itself in the demographic studies. And we also need to understand how miscibility takes its effect with other combinations of species. So I just looked at the most simple sub-Neptune model you can possibly build. But right, how does miscibility behave between water and silica and all these other species? So thank you very much. Happy to take questions.
Okay, questions for James? The one right here in the front. There in the back.
Hi, Marat, Kaptein Institute, Groningen. Thanks for the great talk. I'm interested, can you talk a bit more about like the comparison you made between like the standard evolution of the radius versus the miscible one, and how can you observationally confirm that? Because like we don't have that many very young sub-Neptunes, right?
Let's see. So nearly there. So imagine now that I produced it, right, when we look at young sub-Neptunes, we maybe only have just under 20 of them at the moment. But we see that a lot of them are nearly the size of Jupiter when they're young. They're really, really puffy. So if I imagine building a miscible model that actually starts at the size of these young sub-Neptunes, it's going to contract like this. And so if we start building that population of young sub-Neptunes, we would expect to see that they remain at much larger sizes for a long amount of time. So there's already, I think, some tentative hints that this is actually happening just from planets from tests. But again, we need to understand really how that, once we build up, how many young sub-Neptunes do we really need to try and show that is the idea, and what's the best age range to try and test this. But I think there's some tentative.
Do you have an answer for that already, like a tentative?
No, sorry.
Okay, I saw one more question in the back.
Hey, do you hear me?
Yep.
Guillaume Chavarot from the University of Grenoble. Thank you for your presentation. About the 4,000 K, do you have an idea of how you translate that in terms of distance between the star and the planet?
Yeah, sorry, is the question, so how does this contraction happen?
No, about the constraint on the temperature of the core to have this miscibility. So
I see. Right, so distance from the star isn't going to affect too much the interior temperature profile when you're really deep in the planet. The distance from the star really controls the temperature at the very top of your atmosphere. So it's really a product of how you formed the planet is going to control that temperature. So I think it's probably worth highlighting that that shape of that binodal, that phase curve, is around 4,000 Kelvin, but we've just seen from the previous talk that it might be close to 5,000 Kelvin or something like that. So, you know, there's variation in where exactly it might sit in that phase diagram, but we think the qualitative results should remain in terms of slower contraction with time. So one thing we are looking at is actually then, how does this happen? This is for one planet, equilibrium temperature of 1,000 Kelvin. So what happens when you then vary that across different temperatures? So we're looking into it, yeah.
Thank you.
I have a quick question for you. How is the energy transported in the interior?
So good question. We take the implicit assumption that we have very efficient mixing in the interior, which also then affects how we assume then that hydrogen can mix all the way through the interior. So we're essentially, in model space, we are taking the extreme case that we have very good efficient mixing. And so we're assuming a convective thermal transport in the interior. And again, the idea is to test if miscibility is happening in this very efficient way, how would it present in the demographics? You could conceivably think of an idea where it isn't convective, in which case you have to reconsider, does hydrogen reach all these places? Yeah.
Okay, let's thank our speaker again. And now we have Rob Calder, also from Cambridge, and he will be telling us about, I lost it. Mapping the solidification shoreline for gas dwarf planets.
Right, can everyone hear me? Perfect. Okay, hello everyone. My name's Rob. I'm a PhD student at the University of Cambridge, and I'm going to be talking today about some of our work looking at mapping the solidification shoreline for gas dwarf exoplanets. Don't worry, I'm not going to show you the radius valley again. But still, I think it's worth reiterating the fact that one of the most significant and perhaps surprising results from the Kepler survey is that sub-Neptunes are extremely common in our galaxy. However, because we don't have any sub-Neptunes in our own solar system, there's still a lot we don't know about these planets, primarily what it is that they're actually made of. And this puts sub-Neptunes at the frontier of exoplanet science. Two hypotheses among many for the structural nature of sub-Neptunes are the gas dwarf and water world hypothesis. So with the gas dwarf hypothesis, you have an Earth-like iron silicate interior and a voluminous hydrogen-dominated atmosphere. And for the water world case, you have a slightly smaller Earth-like iron silicate core and a large water mass fraction, and perhaps a tenuous H2 outer envelope. And because both these hypotheses can reproduce the mass radius constraints for sub-Neptunes, we need a way of being able to distinguish between them observationally. One potential way of doing this involves the molecule ammonia, and this was first proposed by Madhu about 3 years ago now. And the argument goes thus: if you have a H2 atmosphere with trace amounts of methane and carbon dioxide, you'd also expect to see ammonia. However, if you have a water world with a liquid water interface with the H2 atmosphere, i.e. a Haitian, the ammonia will dissolve into the liquid water and thus be removed from the atmosphere. And you wouldn't expect this to happen on a gas dwarf because you have a solid surface. So if you to observe the atmosphere of a sub-Neptune in transit spectroscopy and you weren't to see ammonia, then this suggests that this is in fact a water world, and this breaks the degeneracy. However, what if the gas dwarf also had an ocean, not water, but magma? There was a paper from Ollie Shortall a few years ago that proposed that if you had a gas dwarf with a molten surface in contact with the H2 atmosphere, the ammonia would dissolve into the magma ocean, and therefore the two scenarios are degenerate again. But not all gloom and doom. If you have a magma ocean in contact with an H2 atmosphere at a gas dwarf, there would be other interactions between the magma ocean and the atmosphere that could produce observational signatures that could also be used to break the degeneracy, and also at the same time give us some insight into the interiors of the gas dwarfs. So magma oceans and gas dwarfs have significant implications for unveiling the nature of sub-Neptunes. This then leads us to the question, well, are magma oceans a viable outcome on gas dwarfs? How long do they persist? And are they a common outcome across the gas dwarf population? So to answer this question, we use the Proteus modeling framework. It's probably not the first time you're going to see this diagram at the conference. So Proteus is a 1D coupled interior atmosphere planetary evolution model. And the way it works is that we initialize the mantle fully molten and we evolve the thermal state of the mantle using SPIDER. And the output from SPIDER is then passed into Calliope, which is solving for the partitioning of volatiles between the magma and the atmosphere. This then sets the composition of the atmosphere, which is fed into Agni, our 1D climate code, which solves for radiative convective equilibrium in the atmosphere. And so we repeat this process until one of two outcomes are reached. If the global volume melt fraction in the mantle decreases below a certain threshold, we say that the planet has solidified. However, if the net flux leaving the top of the atmosphere decreases below a certain value, then we've reached energetic equilibrium. And if this happens before the planet solidifies, the planet will have a permanent magma ocean. To answer the question of how common magma oceans are in gas dwarfs, we use something that we call the solidification shoreline. And this is analogous to the definition of the habitable zone. So the way this works is that we draw a line in the host star effective temperature and insolation flux parameter space, and we say, okay, any gas dwarfs to the left of this line in the parameter space, we predict will have permanent magma oceans. However, if the gas dwarf resides in this region of the parameter space to the right of the line, we predict that it will solidify eventually. So what we do is we run a suite of Proteus simulations across this parameter space, and we compute the insolation flux at which the end state transitions from a permanent magma ocean to a solidified mantle as a function of host star effective temperature, i.e. the solidification shoreline. And we do this for three different envelope mass fractions, i.e. the mass fraction of the planet that is atmosphere rather than iron silicate interior. And so we can see here that for larger envelope mass fractions, the solidification shoreline is pushed to lower insolation fluxes. And this is because if you have a more massive atmosphere, you have a stronger greenhouse heating rate of the surface. Therefore, you need to move the planet further away from the host star so that it can cool down to the point where it can solidify. What you're seeing here are the positions of all detected sub-Neptunes in this parameter space. And the points are colored by the envelope mass fractions that we predict for these sub-Neptunes based on their mass radiance constraints and the assumption that they're gas dwarfs, all of them. What we then do for each of these detected sub-Neptunes is we calculate the ratio of their observed installation flux and the installation flux corresponding to the solidification shoreline relevant for their host star effective temperature and envelope mass fraction. What this all means is that for a given sub-Neptune, if the value of this flux ratio is less than 1, we expect that this sub-Neptune will have a solidified mantle. However, if the value for a given sub-Neptune of the flux ratio is greater than 1, we expect it to have a permanent magma ocean. We see here that the majority of the detected sub-Neptune population have flux ratios much larger than 1. So we predict here that the majority of the detected sub-Neptune population, if they're gas dwarfs, will have permanent magma oceans. You can also see here the positions of several well-known sub-Neptunes with JWST transit spectra. Chief amongst them, K218b, TOI270d, and TOI836c, amongst others. And we see that all of these sub-Neptunes have installation fluxes consistent with them having permanent magma oceans. So, to summarize, our headline result here is that the vast majority of the detected sub-Neptune population will have permanent magma oceans in their surfaces if, in fact, they're gas dwarfs rather than water worlds or other varieties of sub-Neptunes. And this motivates further work, both experimental and theoretical, to try and understand the interaction between magma oceans and overlying H2 atmospheres and the implications of this interaction on planetary evolution and on observations. We also show that for gas dwarfs, the envelope mass fraction and the installation flux are the two most important parameters that determine the likelihood of a gas dwarf having a permanent magma ocean. And finally, we've shown that for several prominent sub-Neptunes, including K218b, TOI270d, and TOI836c, the installation fluxes for these planets are consistent with permanently molten gas dwarfs. And you can read more about these results and some of the other studies in this project in our paper, which is currently under review and on archive. Thank you very much, everyone, for listening, and I'm happy to take any of your questions.
Okay, questions for Rob? One right here in the front.
Hi, I'm Leonie Jansen from Leiden University. Thank you so much for your great talk. I was curious, you mentioned that you would expect the magma ocean to also have other effects on the atmosphere than, for example, NH3 being soluble. But these sub-Neptunes, they have these really thick atmospheres. So would you still expect to be able to observe these effects of the magma ocean? Or would you think that because the envelopes are so thick, it's way below the observable limits?
Okay, so for the gas dwarf hypothesis, we expect an atmospheric mass fraction of about 1%. So these envelopes wouldn't be as thick as for the water world case, where you have atmospheric mass fractions up to 10 to up to 50%. So we still expect the chemical signatures based on the interaction between the magma ocean and the H2 atmosphere to be observable even in the upper atmosphere.
Okay. Thank you.
Okay, I think Francesca has another question.
Hi, Francesca Miozzi, ETH Zurich. Thank you for the very nice talk. I'm wondering if you tested any compositional effect on your results in regard to the solidification line. Because if you have high volatility solution, you're likely lowering your crystallization temperature. So I wonder if you consider the fact that composition might affect what you're looking at.
Yeah, so we did perform some minor studies where we varied the volatile budget of the material that can partition between the magma ocean and the atmosphere. And we found some slight effect on the location of the shoreline. But we assume magnesium silicates melt, so we don't account for the effect of dissolved volatiles in the melt on the location of the solidus and liquidus, and thus on the melting of the melt. So that is definitely something that we need to look at in future work.
Yeah, thank you.
Okay, let's thank our speaker again. Next talk is by William Misner from Carnegie, and he will be telling us about how rock cloud formation affects sub-Neptune structure and atmospheric composition.
Great. Hi, everyone. I'm Will Meisner. I'm a Carnegie postdoctoral fellow at Earth and Planets Lab in DC. And yeah, I'm going to tell you about rock cloud formation in sub-Neptunes. And to start, yeah, be worried. I'm going to show you the radius valley again. I think this is the 4th time we've seen this plot. And I think it's been mentioned at least 3 or 4 other times. I've been like tallying in my notes. But I mean, the reason we've seen it so many times is because it's really so foundational to our understanding of small exoplanets, right? That we've got the super Earths and the sub-Neptunes, and you know, as James and a bunch of other folks have said already today, right? One theory that has been really good at explaining these observations is if you picture sub-Neptunes as having these silicate-rich interiors surrounded by a hydrogen atmosphere, that can explain the radii of these sub-Neptunes really well. And then over time, if these planets are exposed to atmosphere escape processes, they can turn into these super Earths, these rocky worlds that we're so interested in here, right? And I think that's just important to think about why we care about these sub-Neptunes at a Rocky Worlds conference, right? Because a lot of them are going to become these rocky worlds over time. But to figure out exactly how that happens, we need to consider all the kind of implications that this simple kind of 2 circles drawn on top of each other model has. And you know, people have been talking about a bunch of different ones, but one I like to think about a lot is what if these silicates are evaporating into the atmospheres of these sub-Neptunes? And the reason that we might care about that, if we're wondering how to model these sub-Neptunes, is because that has a big effect on the structure of these atmospheres. Essentially, the idea is that if you have a lot of a heavy condensable species, so something that's heavier than the background gas, and they're condensing as you go deeper and deeper into the planet, as the temperature gets hotter and hotter, that can actually inhibit convection. And it induces a non-convective layer. Once these deeper particles are heavier than they are hot, this is just an equation to show you that I know how to do math. But Yi-Chen actually explained this really well yesterday with waters being the condensable, but this exact same physics happens in the base of these sub-Neptunes where silicates are condensing. And so you can get a structure that looks something like this. So instead of kind of the normal model where you have a convective layer with a radiative layer on top, you actually have this other layer inside the planet just above the surface of the silicates where convection can be inhibited. And yeah, like I said, these physical arguments are pretty universal. They apply to silicate vapor above magma oceans and sub-Neptunes, but also to solar system planets like Saturn and Uranus and Neptune, and to water worlds, as some folks in this room have thought about a lot. If you model this, not only do these silicates change the atmospheric structure of these planets, they also change the atmospheric chemistry of these planets, because if you inject a bunch of silicate oxides into a hydrogen atmosphere, it's going to react with the hydrogen because hydrogen is so reducing. And so what you can end up getting is silicates interacting, turning into water, turning into other silicon-bearing species. And you need to do all this correctly if you want to understand sub-Neptune observations and sub-Neptune evolution. And so that's what we showed in this paper that I led a couple of years ago, where if you do all this chemical and structure modeling all together, just assuming that kind of the simplest possible thing you can do, that if you have silicate oxides evaporating and then reacting with the hydrogen, so it's a chemical equilibrium network with 3 reactions, so that was easier than more, you get this kind of exotic structure. And I'll take you through it piece by piece. We've got number mixing ratios on the top as a function of pressure going out to the right. and temperature on the bottom there. And so a few key aspects is that actually silane, SiH4, is the main silicon-bearing gas species in these envelopes. It dominates over SiO, and the hydrogen, the water, and the silane are actually like very strongly coupled in this model. So like the partial pressure of each, the number mixing ratio of each, are kind of locked together through most of the atmosphere. But that's actually, as I'm going to show, only because we're sort of doing these reactions assuming one silicate condensable is possible, that this SiO2 is the only possible condensable. We have this inhibited region where convection is inhibited, and it goes from, I just arbitrarily set the base of this atmosphere at 4,000 Kelvin, and it goes all the way to about 2,500 Kelvin. And that makes a big difference in the atmospheric structure of these planets if you want to model their radius, right? So the transit radius of this planet, if you model it, is 2.4 Earth radii. But if you assume that it was fully convective, you would get a transit radius of about 2.8 Earth radii. So that's a pretty big difference if you want to infer some Neptune attributes from their radii. You really have to account for this. But like I said, this single condensable framework that a lot of people use is limited, right? Because when you're assuming that that's the only condensate you can have, you're really locking in both the interior composition and the atmosphere composition that you can possibly get. And it means that you're unable to incorporate key atmospheric constituents that are probably going to make a difference for a structure and are really important observable species in these upper atmospheres. So things like carbon, things like magnesium, iron, and basically all the other species that we might see in these atmospheres. And so we want to get better than that, right? And we want to be able to model how all of these different condensables are interacting in a more realistic way in these atmospheres using rainout chemistry. And the way to do that is to couple a more detailed atmospheric chemical equilibrium model, so FastChem, with these existing structure models to capture these non-convective regions and the chemistry and everything self-consistently. And I just want to show you some preliminary results from that work that I'm working on right now. And so first, let's just work with a model that looks pretty similar to what I just showed you, right? So we've got the water and the silane are locked together. Again, we got number mixing ratio, we got the condensate that's condensing out, and we've got the atmospheric structure, the temperature structure again. And so you can actually just barely see it on this, but the water and the SiH4 are like basically on top of each other. So that's good. We can kind of reproduce our previous results. But what happens if we change the base ratio of silicon and oxygen? Well, you can make it really oxygen poor, right? You can increase the amount of silicon relative to oxygen, and then you get a very silane dominated lower atmosphere, right? So the water plunges, and essentially what's happening is all of the oxygen is getting locked up in these oxides that are condensing out, and there's no oxygen left in the upper atmosphere. So all the oxygen rains out. And so, right, we've got silane dominating, and all this different structure, all these different condensables lead to a different structure, atmospheric structure, right? You can see that the non-convective region only goes to like 3,500 Kelvin instead of about 3,000 in this one. And you get a different radius, right? This one planet is only 2.4 Earth radii instead of about 2.6. Meanwhile, if you increase the amount of oxygen, right, you get a water-dominated atmosphere. You get, well, there's still a lot of hydrogen. What did I do? Oh, there we go. We've got, so instead, this is kind of silicate limited, so all the silicates rain out. And you get a water-dominated atmosphere, and you get even a different structure and radius, right? So this one, instead of being 2.4 or 2.6, you get this planet is much smaller because it has such a high mean molecular weight due to the amount of water you get that you get a very different atmospheric radius. And these, I should note, right, these all have the same amount of hydrogen in the atmosphere, and they have the same base temperature, and they have the same equilibrium temperature and planet mass, right? So the same planet, the same hydrogen gets you 3 different radii based on exactly what the ratios of species are at the bottom. But you can do even better, right? You can expand to include things like magnesium and carbon. And then you get this, you can get huge diversities in the different condensates that are all interacting with each other, condensing at different regions of temperature and pressure. So now we've got this whole kind of smorgasbord of magnesium oxides and silicon oxides, and even silicon carbide can condense at low temperatures and pressures if you have enough silane and carbon mixing together. And depending on your silicon magnesium oxygen ratios, again, you can get very tremendously different atmospheric structures and atmospheric sizes and atmospheric compositions, right? So this one ends up being more carbon and water dominated. This one ends up being silane dominated, except it starts raining out at upper species. So this depends kind of where the quenching happens, and also other species like methane and magnesium and things like that. And so I'm still kind of in early stages of exploring our parameter space and making, testing out how these inferences change with things like equilibrium temperature and atmospheric mass fraction. But I think these are really promising results that show that you really need to think about all the things that are happening deep in these sub-Neptune atmospheres, all the possible condensates you can have and how they affect the temperature and the pressure structure that you want if you want to understand these sub-Neptunes over time. So that will just about, wrap it up. So just what I want you to take away from this is that you really need to consider these magma-atmosphere interactions deep in these sub-Neptunes because they're really important for understanding the thermal structure and therefore the size of these planets over time because of this convective inhibition effect. The outgassed magma species aren't going to say as oxides necessarily. They're going to react with the hydrogen. And that's going to change the composition of the atmosphere and its radius. And this is a really promising way to say, how are we going to understand how these planets evolve in time? How are we going to infer their compositions from their both the observations with JWST and just how their radii evolve over time. Some really promising directions in the future are thinking about upper atmospheric physics like quenching, and then thinking, I'm just throwing this in because I also like atmospheric escape, so come talk to me about atmospheric escape, because all this affects atmospheric escape, and if you want to know more about that, just come talk to me. Thanks a lot.
Great. Questions? So while you are thinking on your questions, just a comment about the criteria on the convection inhibition. I'm trying to promote that we call this the Guillot criteria, because I think the paper is brilliant. It has very elegant math. It has lots of applications, and Tristan Guillot is too humble to propose it himself. So it would be a simple way for all of us to know what we are talking about.
The problem with that is that he's invented too many things. And so it'd be hard to know which it is.
Okay, questions? Yeah, Tad.
Hey, Will, great talk. Tad Kamasik, Oxford. So yeah, this is really exciting how you're including a variety of condensables. And you showed some nice distributions of the condensables like as a function of pressure. And I was wondering basically, how can you explain how you treat the mixing of all the various cloud species in your model and the prescription that you're using?
Yeah, so I am just doing kind of rain out equilibrium at every point in the profile. So I'm not really assuming any like diffusive mixing of cloud condensates, but that would be a really interesting thing to kind of think about. Basically the assumption, and I think it's okay, but I'd love to talk about it more, is that at these kinds of temperatures and pressures, chemistry is probably very fast. And so I'm basically making the end member assumption that that's always the fastest time scale in the problem. But it'd be cool to think about that more.
Yes, question here in front.
Marati, Kaptein Institute Groningen. Thanks for the great talk. About that convection inhibition criteria, I maybe didn't have time to properly see the math equation that you put. But like, isn't that like similar to the Ledoux criterion that's used for stars?
I mean,
it's similar, but yes, you're right on. You also have that. It's quite similar. There's one difference, which is that the mu here, it's kind of implicit. So maybe actually, I'd have to think about it slightly, but I'm pretty sure the way of framing it like this is essentially the Ledoux criterion. But the difference is that mu depends on T, whereas in the stars, mu is sort of independent of the temperature. But here, right, because we're thinking about condensable species, the mean molecular weight of the gas depends on the temperature, because the higher the temperature is, the more of the condensable evaporates into the gas. And so that changes the way you calculate this criterion, essentially. But you're right to pick up that it's very similar.
Okay, let's thank our speaker again. And now our last talk of this session is Aaron Werlen from LMU in Munich, talking about magma oceans and the fate of water in super Earths and subneptune.
Great, thank you so much, Amelia. So I will now be talking about the water content of super Earths and subneptunes, which is based on a paper we published last year in APJL. Before I can show you the results, we first have to establish where the water actually comes from. And of course, as you all know, planets fall in protoplanetary disks, and depending on the formation location of the planet will accrete different volatiles. So for example, if a planet forms outside the so-called snow line, which is the H2O condensation line, it can accrete a lot of water, whereas a planet who forms inside the condensation line cannot do so. Of course, it's a bit more complicated because planets can migrate, the snow line can move, and so on. But the first order, this is not a bad assumption. And of course, this idea of volatile-rich planet forming outside and then migrating inwards have promoted the idea of water-rich or so-called Haitian planets, which are planets who can accrete a lot of water in the outer system and then migrate inwards. And they're assumed, according to models done in 2021, to have water mass fractions of about 10 to 90 weight%. As a comparison, the Earth has a water mass fraction of roughly 0.02 weight%. And then if the conditions are exactly right, there could be a liquid layer of water between high pressure ices in the supercritical envelope, and this water has been proposed to be able to host life. But of course, these models neglect a very basic concept, which is the interaction between the atmosphere and the interior. Because we do know that subneptunes and super Earth with a few weight% of hydrogen envelope can be molten for very long time scales. And of course, if you put stuff under pressure and it's hot, it's going to react with the surroundings. So water, for example, that is being accreted onto the planet can chemically react. It can partition into the interior, for example, the melt or the metal phase, and can therefore change phases, and the water content might be changed. So the question, of course, remains is how much water is actually geochemically plausible. And to do that, we use the global equilibrium model, which is a model for super Earths and subneptunes in global chemical equilibrium. By global chemical equilibrium, we mean an equilibrium between a planetary gas phase, silicate phase, and metal phase. And in total, we calculate an equilibrium network with 26 phase species and 19 linearly independent reactions. And I don't want to bother you with the math, so I'm going to show you schematics of how the model works. We define in total 7 components for the bulk composition. These are, for example, the modes of silicon, oxygen, magnesium, and hydrogen. We define the temperature. We define the temperature at the surface or at the magma ocean atmosphere interface, as well as the silicate metal equilibration temperature. And then at the end, we define the planet mass. And ultimately, we end up with the chemical composition of the silicate mantle, the metal phase, which can be thought of as the core for smaller planets, and the envelope. And you can see that we, for example, account for volatile species in the silicate phase, like hydrogen, CO2, and water, but also for refractory species in the gas phase, like sodium, magnesium, iron, and SiO. To get from A to B, we need to solve for chemical equilibrium for the 19 chemical reactions, and we also involve mass conservation, number conservation of each phase. We're currently working on a publication of the code. There is already a public version, which was published by Ed Young in 2023. We improved the code in terms of speed and modularity, and we hope to be able to release the code in spring this year. And of course, we now need to inform the initial composition of the planets. And for that, we use the so-called next generation planet population synthesis model, which is a planet population synthesis model. In easy terms, this is just the output from the so-called Bern model, which some of you might be familiar with. This is a self-consistent framework to model planet formation. In total, they distribute roughly 50 to 100 planetesimals. They do the N-body simulation, and they also track the accretion of ices like H2O, CO, CO2, and other carbon and oxygen compounds. And they also include migration. On the right-hand side here, you can see an easy schematics of how the model works. And by looking at it, you might figure out why the PhD student at the University of Bern call it the beast. So now we couple the NGPPS with the global equilibrium framework. And we do that by first extracting a population from the planet population synthesis model at birth, at roughly 20 megayears. So this is a very young population. We then select all planets between 2 and 15 Earth masses, so Earth or sub-Neptune regime, and surface temperatures between 1900 and 4000 Kelvin. We then plugged these planets, or the composition of these planets, into the global equilibrium framework, and we calculate the composition of the gas, the silicate, and the metal species, as I showed before. And then from this, we calculate the water mass fraction, which is the water in the gaseous phase and the silicate phase. At the same time, we extract the water mass fraction from the birth population, and then we compare the two. And the results look like this. So on the x-axis, we have the accreted water mass fraction. On the y-axis, we have the equilibrated water mass fraction. If there would be no chemistry happening in our universe, all of these planets would line up on this line. We can clearly see that that's not the case. And we can see the planets, even though they can accrete a lot of water, up to 38%, ultimately end up with very little water compared to the initially accreted water of roughly 1.5 to 2 weight%. Again, as a comparison, this is still 3 orders of magnitude more than the Earth. So it's still a lot of water, but it's not enough to meet the hydrogen threshold of 10 weight% and above. And then, of course, we can also look at the atmospheric composition of these planets. If you do that, for example, if you look at the H2O mass fraction, the envelope, against envelope mass fraction on the x-axis, you can see that there is a clear trend. So planets with small envelopes can have a lot of water in their envelopes, proportional to their small envelopes. These are small envelopes with a lot of water. If you then increase the hydrogen content, so if you increase the envelope mass fraction, the water mass fraction reduces. And this makes intuitive sense, because if you remove the hydrogen, you will be more sensitive to the metals, like H2O. So it's sort of, when you burn the haystack, you will find the needle. And in addition to that, you can see a clear correlation of C to O ratio. And the bulk C to O ratio, of course, is a tracer of formation location. So if you take this figure and plot it against orbital or formation location and separate it for planets that formed inside and outside the ice line, you can see the planets who predominantly formed inside the ice line can have large water envelopes or small water-dominated envelopes, whereas planets who form outside the ice line do not have that. And this is, of course, in contradiction to at least some planet formation models, which will predict, at least for early populations, that you can only have water-dominated envelopes in the outer system, not in the inner system. Great. We have published all of these results in a paper in APGL titled Sub-Neptunes Are Dried in the Seam, Rethinking the Origins of Water-Rich Worlds. I want to give shout out, of course, to the co-authors and my supervisors, namely Karen Dorn from ETH, but also Edward Young and Tilke Schlichting from UCLA, who had to develop this study, and Remo Byrne, who provided the data from the NGPPS, as well as Simon Grimo helped with coding problems. Before I jump to the conclusion, I want to quickly do a little advertisement for a session at Goldschmidt will be proposed. Goldschmidt is a big geochemistry conference, which will be held in Montreal between the 12th and the 17th of July. And we propose a session with the goal to make astrophysics and geochemists talk. As you could probably see from this talk, it's important that these disciplines talk more and try to exchange ideas. So if you work on any of these related things, please consider submitting an abstract. The abstract submission is open now, and the deadline will be February 26th this year. Okay, let me show you the conclusions. So we coupled the NGPPS and the global equilibrium model, and we calculated the H2O content. We find the magma-ocean-atmosphere interaction destroy most of the accreted water. We find that all planets fall short of the hydrogen threshold, as you can see here. And we find that only small envelopes from inside the ice line can be H2O dominated. And of course, this is sort of defined of classic planet formation theory, which will predict high H2O contents only in the outer system. And these results demonstrate that the next generation of planet populations in this model need to account for the interaction between the envelope and the interior. And with that, I'd like to end, and I'm happy to take any questions.
Questions? You are all being very shy before lunch. Okay, I have one.
Yes.
I was wondering, you are using chemical equilibrium, but when you are very deep in the planet, you don't have ideal fluids anymore.
Mm-hmm.
So how do your results are really affected by the fact that you have real gas?
Yes, so we do account for non-ideality in the metal phase for oxygen and silicon, but we have a paper in review at the moment where we implemented non-ideality also in the silicon, the gaseous phase, and we find that the results, at least of first order, are not extremely sensitive to the non-ideality.
So it doesn't matter that you don't have equations of state and quantum things happening down there?
I mean, what we find is that if you add non-ideality only to one phase, for example, the gaseous phase, the results will change. But for example, if you then add activity coefficients for volatile species in the silicate phase, these effects can be counteracted. So we do not find a big sensitivity to non-ideality.
Okay, interesting. Any other question? Okay, now you got these two, and then we go to lunch. Yeah, chat and chat.
Charles-Edouard Boucaré, York University. Do you assume that all the different layers, let's say atmosphere, silicate, metal, are all in equilibrium?
Sorry?
Are they all in equilibrium?
Yes, yes. So the whole, I mean, basically what we get back are the abundances above the magma ocean, right, at the end of the code. So we do not radially resolve the structure of the atmosphere. But we assume that all of the hydrogen is in equilibrium with the magma ocean. Yes.
And you mentioned also that metallic phase. Is it
Yes.
Is it a core or metallic core that you have in mind or something?
I mean, the metallic phase could be the core, but of course the silicate metal equilibration does not happen at the core mantle boundary. It happens higher up in the mantle, maybe like 20 GPa and a few thousand Kelvin above surface temperature. So it's not exactly the metallic core. It's more the metal phase within the silicate mantle.
I see. Right. Thank you so much.
Thank you.
Okay, I think Tad had a question.
Hi, Tad Kamasic, Oxford. So I really like the coupling with the Baron-Popsynth model. And I guess to me, it's surprising, of course, as you said, that there's not very much water for planets that form beyond the ice line. And I guess I naively would have expected late accretion of water, you know, from KBOs coming in or something like that. And so how does the coupling work in terms of the timing? Like, is there a time at which you stop assuming it's in equilibrium? And can you explain that a bit more?
We couple the population after 20 mega years. Right, so the disk just evaporated, so there can't be any delivery of water through asteroids, for example. But of course, optimally, what you would do is you would couple the model, and then you would do the evolution with the Bern model, and then you would recalculate the equilibrium. And we are planning to do that in a subsequent study. Thank you.
Okay, let's thank our speaker again. Before we leave, we have an announcement.
Yeah, thanks. So we'll host this pub quiz night at Café de Tutor. Please do come. There's no registration needed, just come. The doors open at 8. The pub quiz will likely start at 8:30. There will be like several question rounds and prizes for the winners. And also please have in mind that 5 persons per team will be accepted. And yeah, and you'll have fun, please.
Oh, and just for clarity, this pub actually has a very nice selection of malt whiskies. So feel free to enjoy some drinks tonight. Hope to see you there. No, you don't need to bring your badge now.
Come as you are.
Right. Okay, now we have lunch and we come back at 1:30.
Okay, thanks everyone. Let's start the afternoon session now. Welcome back after lunch. I'm Ollie Shortall, and I'll be chairing the session this afternoon before we move into the breakout sessions. So it's my greatest pleasure to introduce Daman Goral, who's joining us from Yale University today. I think Daman's research is an absolutely perfect fit for the Rocky Worlds discussion series. Daman has an absolutely exquisite set of skills ranging from experimental petrology through to making extremely challenging observations of solar system materials. And Daman has used these to really deliver fascinating insights into the origin and evolution of planetesimals in the solar system, their oxidation states, the way volatiles are partitioned and move through them. So I think really fundamental observations for many of the things that we're interested about in the Rocky Worlds community, whether it be solar system or exoplanetary evolution. And iron meteorites in particularly are something Daman's been looking at in recent years. So I'm really excited to hear his talk today, using iron meteorites to trace the origin of volatiles in the earliest inner solar system planetesimals. So thanks so much again for joining us, and take it away.
Thank you. All right. My main challenge is so that you guys don't fall to sleep. So I'll keep it very slow. And I think this is going to be more on the cosmochemistry side of things, but I'll try to I'll try that you guys get something out of this particular talk, because I'm going to be using a very interesting proxy that I've been using over the last, or developing over the last 4 to 5 years, and kind of fundamentally challenges a lot of our current understanding based on the origin of volatiles on the rocky planets. So Earth is the only habitable planet that we know of in our solar system and beyond. In addition to the presence of superficial liquid water, the composition of the Earth's atmosphere, primarily composed of nitrogen and with trace amounts of carbon, plays a critical role in defining the surface habitability of a planet. Sorry. Yeah, that one. This is not. It's not working. That's okay. Yeah, that's fine.
The arrows.
Okay, that's fine. All right. And also nitrogen, nitrogen, carbon, and water are also primary components of the basic building blocks of life on a planet. If we truly want to understand the habitability of a planet, we need to understand the origin of these 3 key life essential volatiles on the present-day superficial reservoirs of a planet. But we know that Earth is a tectonically active planet, which means over billions of years of Earth's history, the exchange of volatiles between the Earth's interior and surface reservoirs has set up or controlled the abundances of the volatiles in the present-day superficial reservoirs of a planet. So basically, you can have ingassing of volatiles during the subduction, and then you could have outgassing of volatiles during volcanoes and other things. So basically, you have this exchange between the interior and superficial reservoirs, which controls the abundances of these volatile elements or the surface reservoirs of a planet, which are important for habitability. So if we truly want to understand the origin of volatiles in the present-day superficial reservoirs of a planet, we need to track the origin of volatiles in this big box over here, termed as the bulk silicate Earth, because over billions of years of Earth's history, that this exchange in between of volatile elements in these reservoirs controls the surface abundances of these volatile elements. Of course, these elements are present in the metallic core of the Earth, but it is generally assumed that the exchange of volatiles between the Earth's core and mantle is not that efficient. So basically, you have to track these reservoirs over here. The origin of volatiles in the bulk silicate Earth is generally tracked by isotopic fingerprinting. So what you do in this particular case is you take the stable isotopic composition of a particular volatile element in the terrestrial reservoirs, and then you compare it to different cosmochemical reservoirs. So the representation is on this parts per thousand notation. You have the isotopic composition, the stable isotopic composition as sample, normalized to some standard, and this is the parts per thousand notation. So you have on the y-axis, the nitrogen isotopic compositions. On the x-axis, you have the hydrogen isotopic compositions. So if you look at the nitrogen and hydrogen isotopic composition, the bulk silicate Earth, this red star over here, it is completely distinct from the nebular gas. So this is the gas which primarily makes up the sun. It's the primary volatile reservoir in the solar system, but the isotopic composition is different. It also is different from the cometary ISIS over here. But if you look closely over here, the nitrogen and hydrogen isotopic composition of bulk silicate Earth, it plots in a similarish kind of a range as different classes of chondrites. So chondrites are these primary building blocks of chondrite sample, the early solar system planetesimals. They sample the primary building blocks of rocky planets. So basically from this plot, you can say that the first from planetesimals in the solar system and the final rocky planets, they had a common origin of volatile elements. But if you compare the abundances of volatiles in the bulk silicate Earth relative to the most primitive materials in the solar system, which are these CI chondrites, you see that the volatiles in the bulk silicate Earth are extremely depleted relative to the most primordial materials in the solar system. So there is a depletion of 2 to 3 orders of magnitude relative to the most primordial materials in the solar system. So you basically have contrasting pieces of observation over here. On one hand, you have this isotopic similarity, but on the other hand, you see this extreme volatile depletion. So how do you put these 2 pieces of evidence together? So if you look at a chondrite, it looks something along these lines. So this is basically a rock almost like a sedimentary kind of a rock where you have different disequilibrium assemblages kind of connected together. So you have high temperature condensates like CAIs, chondrules, and metals. They do not contain any of these volatile elements because they're condensed at very high temperatures. And then you have this dark colored matrix, which is primarily composed of hydrated minerals and organics. So this is where the volatile elements reside. But if you look at a fully formed planet like Earth over here, you see it does not look anything like that of a chondrite. So basically, if you truly want to track this journey from this scale, from chondritic scale, to a fully formed planet, we need to understand the formation of planet itself. Like we need to track the journey of the formation of the Earth itself. So this journey, so this cartoon was inspired by one of Paulo Sossi's talks. So basically, what you have over here is a simplified representation of the formation of rocky planets in the solar system. So basically, you have in the early solar system at t is equal to 0, a protoplanetary disk, primarily composed of gas and dust. Then somehow, these dust particles start to clump together to form planetesimals, 100-kilometer sized bodies. We don't know exactly. There are processes like streaming instability that might have taken place, but somehow these planetesimals start to form very, very early. Now, there is a very important, interesting phenomena in the early solar system, because when these planets form, they inherit a very important short-lived radioactive nuclide, which is 26 aluminum. So this radioactive element is going to play a very important role in this particular talk. So 26 aluminum has a half-life of 0.7 million years, and it is present in substantial enough quantities in the early solar system so that the planetesimals which accreted within the first couple of million years of the formation of the solar system, they could have undergone large-scale melting because it could supply enough amount of heat. So basically, at the very early stage, you can go from undifferentiated rubble pile-like asteroids to differentiated planetesimals, almost like baby planets which have their cores and mantles. And in this talk, core means a metallic core. That's what I'm referring to. So basically, you could have this differentiation taking place very, very early stage. And then you have the later stages of planet formation. So basically, you have collisions among these kind of bodies, and then you eventually form fully from rocky planets. I'm not going to go into the debate of whether it's a pebble growth or that's not important, or it's planetesimal, but that's not important for my talk. Because what I'm going to do today is I'm going to focus on these early stages of the solar system formation, within the first couple of million years of the formation of the solar system. And I'm going to try to convince you that this stage actually shapes up the volatile budget of rocky planets in our solar system. So the guiding question in my talk is going to be, how can the earliest solar system planetesimals that accreted extremely early, how can they shed light on the origins of these three key life essential volatiles on Earth? To answer this question, let us take a step back and look at our current understanding of the initial architecture of the solar system. So based on the nucleosynthetic anomalies of several non-volatile elements, we know that meteorites plot in two distinct clusters. So this is called the classic isotopic dichotomy of the early solar system. So you have blue-colored meteorites over here, which sample the outer solar system reservoir. And then you have the red-colored meteorites over here, which sample the inner solar system reservoir. So basically, you likely had a solar system that was divided into two distinct reservoirs at very, very early stages of solar system formation. Within the first couple of million years of the formation of the solar system was divided into two distinct reservoirs. So this color scheme I'm going to follow during the entire talk. Blue always means outer solar system, and red always means inner solar system. So if you look closely at terrestrial planets, where do they plot in this particular plot? So basically, if you see Earth, it almost plots in the inner solar system cluster, which means terrestrial planets like Earth are mostly made up of inner solar system materials with very small contribution from outer solar system materials. Almost 95% of the Earth was made up of inner solar system materials with very little contribution from outer solar system materials. And also another important observation, if you look over here, you look at the accretion ages of these chondrites over here. So they sample planetesimals that formed around 2 to 4 million years of the formation of the solar system. But from planet formation models, as well as meteoritic evidence, we know that the seeds of the rocky planets started to form right at the onset of solar system formation. And so these meteorites do not sample those earliest forming seeds of the rocky planets. So there is another class of meteorites that can come to a rescue in solving this problem, and that meteorites are iron meteorites. So iron meteorites sample the earliest formed planetesimals both in the inner and outer part of the solar system, and these planetesimals likely started forming almost at the onset of solar system formation. So what are these iron meteorites? So as I said, if planetesimals form early enough, they're going to accrete enough 26 aluminum to undergo large-scale melting and differentiation. So what I mean by differentiation over here is the planetesimal is going to melt, is going to reach a magma ocean-like stage, and the metallic droplets are going to segregate out from the silicate melt to form the metallic core. And before this segregation, during those high temperatures, the volatile elements, there could have been equilibration of volatile elements between the metallic melt and the silicate melt before the formation of the metallic core. So basically, the metallic core during this metal-silicate equilibration can record the chemistry of the bulk planetesimal. So you can retrace that chemistry. And iron meteorites actually sample these metallic cores. So these planetesimals, they differentiated. Eventually, they would have cooled down. Then you have disruption of the bodies, and then you have meteorites that come from the metallic cores of these planetesimals. So as I said, Earth is mostly made up of inner solar system materials. So what we are going to focus in this particular talk is looking at the compositions of these iron meteorites. Iron meteorites that sample the inner solar system planetesimals. What did they look like? What did their volatile budgets look like? So the classical understanding is that during the earliest stages of the protoplanetary disk, the inner parts of the disk should have been extremely hot. So the disk was so hot, you could not be condensing any of these volatile elements from the gases into the form of solids. So basically, in these regions where these planetesimals must be forming, they should be accreting in regions where the temperatures are so high that you could not have condensed any of these volatile elements in the form of solids. So the classical understanding is that these planetesimals should have been volatile-free. They should have accreted from volatile-free materials because you're not condensing these volatile elements out of the gas because the temperature is so high. And the outer solar system planetesimals should be volatile-rich. So basically, the idea is that the building blocks of planets were volatile-free, so you could supply volatile elements only from the outer solar system to explain the volatile budget of the Earth. So if you take this understanding further, one would say if the planetesimals were volatile-free, then the cores that should be forming should also be forming volatile-free because you're not accreting any of these volatile elements. So now if you take this understanding from the astrophysical models and start to look at the meteorite data, what do we see? So here we are going to look at the carbon and nitrogen abundances of iron meteorites. So this is a typical Caltech-like plot. So you have only one axis. We are looking over here at the carbon abundances of iron meteorites. Each symbol over here represents a unique planetesimal. Again, red inner solar system, blue outer solar system. What do you see in this particular plot? The red color symbols also have carbon, and in some cases, they have more carbon than the blue-colored iron meteorites. So basically, the inner solar system cores, they contain at least similar or higher amounts of carbon than the outer solar system iron meteorites. And the same story holds for nitrogen as well. So the inner solar system cores are not carbon and nitrogen free. They contain substantial amounts of carbon and nitrogen. For comparison, if I plot the carbon and nitrogen abundances of bulk silicate Earth, they are not insignificant numbers. They're important numbers that we see in these planetesimals. So the next question arises, what is the source of this carbon and nitrogen in the first form planetesimals in the inner solar system? What are they sampling? So to look at that, we again went back to the isotopic compositions. So what you see over here are the nitrogen isotopic compositions plotted on the y-axis. Don't worry about the x-axis. Just focus on the y-axis. So what you see in this particular plot is that the outer solar system iron meteorites, they have distinct nitrogen isotopic composition relative to the inner solar system iron meteorites. So you have nitrogen isotopic compositions that are much lighter or more negative than the outer solar system iron meteorites. So there is not only a source of carbon and nitrogen in the inner solar system, but that source was isotopically distinct from the outer solar system. And because carbon and nitrogen in the most primordial materials are present in the form of organics, so there were organics present in the inner part of the solar system that were accreted by these first form planetesimals. So basically, there has to be some organic synthesis in this part of the disk, and these organics have to survive to be accreted by the planetesimals because the temperatures were so high, these planetesimals should not have accreted much carbon and nitrogen. So this kind of brings into question our current understanding of how hot was the inner part of the disk. if these planetesimals were forming exactly in the inner part of the disk, as we see from their isotopic signatures. So the next question is, what does it have to do with the origin of nitrogen in Earth? Okay, the first formed planetesimals in the inner part of the solar system, they were accreting nitrogen. But is it an important source of nitrogen in the bulk silicate Earth? So again, we are looking at a classic Caltech plot, so you only have one axis over here. So what you look at over here is the nitrogen isotopic composition of different solar system materials. So let's go step by step. So you have outer solar system materials over here represented by blue color. The empty symbols are iron meteorites. The filled symbols are chondrites. So the outer solar system iron meteorites plot in a similar-ish kind of a range as that of chondrites. So they capture a similar kind of isotopic composition range. If you look at the inner solar system chondrites, they capture this range that is up to -20, -25 per mil. But if you go to the inner solar system iron meteorites, they capture a much more negative composition. Those numbers could be as low as -80 per mil. Why is this important? If you look at the nitrogen isotopic composition of the Earth's atmosphere, it's over here. And if you look at the nitrogen isotopic composition of the Earth's mantle, it is much more negative. And you cannot explain the nitrogen isotopic composition of the Earth's primordial mantle without the accretion of these kind of materials. So basically, this tells us is that you need the accretion of these kind of materials to explain the nitrogen isotopic composition of the bulk silicate Earth, which tells us that there must have been a dual origin of nitrogen on Earth. So this leads to an important conclusion, that the earliest inner solar system planetesimals, they were not only inherited locally sourced organics, but these kind of organics also contributed to the nitrogen budget of the Earth. I have not shown the data for carbon over here, but the same story holds for carbon. So basically, the first part of the talk, the key message over here is that the first planetesimals in the inner solar system, the earliest planetesimals, they were accreting nitrogen and carbon. So they were organics present in the inner part of the solar system right from the onset of solar system formation. And these organics were also contributing somehow to the volatile budget of the bulk silicate Earth. So the next question is, what about water? So now the story of water is a little bit more complicated because under those set of conditions where planetesimals undergo core formation, hydrogen is not a metal-loving element. For carbon and nitrogen, the story is relatively simple because during core mental differentiation, carbon and nitrogen want to go into the core. So you can just look at the core measurements and then you can try to synthesize a story about the origin of carbon and nitrogen. But the story of water is more complicated because hydrogen does not want to go into the metallic core. The measurements are much more complicated. So how do you resolve this? So before going into the origin of hydrogen in iron meteorites, we need to look at another fundamental problem in the early solar system, that is the planetesimal formation in the disk itself. So the general idea is that for streaming instability to work, to form the earliest solar system planetesimals, the dust-gas ratio in certain regions of the disk, where you have to have efficient planetesimal formation, you need to increase the dust-gas ratio by almost an order of magnitude relative to the canonical solar nebula value. And water snow line in the disk is one of those regions that has been postulated to be one of those regions where you can increase the dust-gas ratio in the disk. So basically, the idea could be explained simply as such. So basically, you have icy pebbles that are drifting inwards from the outer part of the disk. As they're drifting inwards, the temperature keeps on increasing. And at a certain point of time, you would hit the water snow line. When you hit the water snow line, these pebbles would start, the ice would start to sublimate, the pebbles would start to disintegrate. And the pebbles, when they start to disintegrate, you have smaller pebbles, so which have smaller drift velocity. So you create some sort of a traffic jam in those regions of the disk. You could also have evaporation, you have water that comes out that evaporates and the disk is turbulent, so you can recondensation of water over here. And the sticking efficiency of these water-being pebbles is also pretty high. So what the point over here is that in these regions of the disk, around the water snow line, you could have efficient planetesimal formation. So basically in this region of the disk, you could have planetesimal formation taking place. And the materials that were leading up to the formation of these planetesimals, they were ice-bearing pebbles over here. So Tim had a paper a few years ago looking at this particular problem, and then he tried to combine it with the meteoritic record. So what he kind of showed in this particular paper was that the water snow line, the movement of the water snow line could have triggered planetesimal formation both in the inner and outer solar system reservoir. So basically, in the class 1 stage of the disk, when the disk is expanding, the temperature keeps on increasing. So basically, the water snow line migrates outward. So basically, you could have the first inner solar system planetesimals forming in the outward during the outward migration of the water snow line. And then during the inward drift of the water snow line, you could see the planetesimal formation in the outer solar system. So in this case, both the inner and outer solar system planetesimals should have been forming at the water snow line. So this model was used to explain this iron meteorite data because the inner solar system iron meteorite parent bodies, they have older accretion ages than the outer solar system iron meteorites. That comes from the core formation ages. But then other geophysical models predicted that actually, if you rerun the core formation models and the accretion models of these bodies, the accretion ages of these planetesimals could also have been early, extremely early, right at the onset of solar system formation. So how do you explain that? So there were a couple of papers that came out the next year. So basically, they argued that to explain the contemporaneous accretion of both the inner and outer solar system planetesimals, they must form at two different regions of the disk. The outer solar system planetesimals are again forming at the water snow line, but the inner solar system planetesimals are forming at the silicate sublimation line. So you could think of a silicate sublimation like, so these pebbles are now drifting inward. So now they're composed mainly of silicon, magnesium, rock-forming elements. And when they cross a temperature barrier of 1400 Kelvin, they again disintegrate to even form smaller pebbles. So basically, now you have contemporaneous formation of planetesimals at two different regions of the disk. Planetesimals forming at the water snow line, and another, the planetesimals forming at the silicate condensation line. So these two models would have completely different predictions for the compositions of the first formed planetesimals in the inner solar system. In the first model, the planetesimals, the earliest formed planetesimals in the inner solar system, they need to form at the water snow line, and they should be accreting water-bearing materials or ice-bearing materials. In this case, these planetesimals should be forming at the silicate condensation line, and the temperatures are extremely hot that you could not be condensing any of the volatile elements in this when these planetesimals were forming. So how do you resolve these different astrophysical model predictions? So again, we'll look back at the meteorite data and ask this question: what do the meteorite compositions actually tell us? Were these planetesimals forming at the silicate condensation line, or were they forming from ice-bearing materials at the water snow line? So basically, let me take a step back and explain to you what is actually kind of going on over here. So basically, think about, you start with a planetesimal. These balls over here represent some siderophile elements. The planetesimal undergoes differentiation. So basically, what you see in the meteoritic record is that the outer solar system iron meteorites, they have higher concentration of siderophile elements, and the inner solar system planetesimals have lower concentration of siderophile elements. So think about in a manner so that you start with same number of balls. If you have a larger room, if you have a larger room, so there would be a lower concentration of those balls, and if you have a smaller room, there would be a higher concentration of these balls. So basically, this kind of tells us is that the higher concentration of siderophile elements over here, because the concentration is higher, it means the metallic core is smaller. In the other case, the concentration of siderophile elements is lower, which means the core is larger. This is what we see from the iron meteoritic record. Larger cores in the outer solar system and smaller cores, larger cores in the inner solar system and smaller cores in the outer solar system. So what it simply means is the metallic core is primarily made up of iron. So if you have a larger core, it means you have more iron in the core. And if you have more iron in the core, that means there is less iron that is missing. But if you have less iron in the core, it means there is more iron missing. The iron must have stayed somewhere. So that iron should be in the form of FeO. So iron can exist as Fe and FeO. So if all the iron is in the form of metallic iron, it would segregate to form a core, and it would eventually form a larger core. But if some iron is oxidized, in this case, you would form smaller cores because some of the iron is residing in the mantles of these bodies. So if you look, so basically what this would predict is that the inner solar system planetesimals, they must have accreted from reduced materials because most of the iron is reduced. And most of the planetesimals in the outer solar system should be accreting from oxidized materials because most of the iron is oxidized over here. This is a relative comparison over here. And because simply water is the main oxidizing agent in the early solar system, you would say that the first form planetesimals, they have to be water poor, and these planetesimals have to be water rich. But if we go by the idea of silicate sublimation line, the temperatures have to be so hot, you're condensing, the planetesimals are accreting from materials condensing at 1400 Kelvin, where you should not be accreting any ice. So the materials you should be accreting should be water-free materials. And in that case, if the materials are water-free, in the nebula, most of the iron is going to accrete in the form of metallic iron that is controlled by the C by O ratio of the nebular gas. So most of the iron is going to be in the form of metallic iron, which means that there should be no FeO in the mantle, because if you're not accreting any water, you cannot oxidize any iron in these planetesimals. On face value, this observation should be pretty simple if we could measure the FeO contents in these planetesimals. But nature always throws curveballs. In the earlier solar system planetesimals, we only have samples from the metallic cores. We do not sample the mantles of these bodies. So we cannot solve this problem in a direct manner. We don't know the answer, why is it so, but we don't sample those mantles. So we have to come up with an indirect logic to solve this particular problem. So this indirect logic is by looking at the abundances of 3 key siderophile elements, iron, nickel, and cobalt. These elements behave almost identically during any astrophysical process, during condensation and so on and so forth, but during core formation, they start to behave in a different manner. So what happens is during any kind of planetesimal core formation condition, all the nickel and cobalt actually partition into the core. So all the nickel that is present in the planetesimal, it would eventually reside in the core of the differentiated planetesimal. But for iron, the idea is very interesting. If the planetesimal is very reduced, it did not accrete any water, all the iron should be reduced iron, so there should be no iron in the mantle of those bodies. But in the other case, if it is oxidized, you could have some iron in the mantles of these bodies. So one could start to make these kind of predictions. So if our idea is correct, what you should be predicting is that the cobalt by nickel ratio eventually of the core that should form should be exactly identical to the cobalt by nickel ratio of the bulk, because all the cobalt and nickel actually partition into the core during the core formation conditions. And this is what we see from the meteoritic record. So over here, you're looking at the nickel and Ci chondrite normalized abundances, and the cobalt by nickel ratios are approximately equal to 1. But for iron, the story is pretty interesting. If these planetesimals were accreting at the silicate condensation line, all the iron should be in the form of metallic iron. So basically, the iron by nickel ratio of the bulk should be identical to iron by nickel ratio of the core. They should be same. But if the planetesimals are forming at the water snow line, there must be some iron missing in the cores of these bodies. So the iron by nickel ratio of the core should be lower than the iron by nickel ratio of the bulk. So what do we get from the meteoritic record? So if you plot the meteoritic record over here, you see that the iron by nickel ratio of the outer solar system iron meteorites is actually lower than 1, which means there is definitely some iron missing in the cores, which must have resided in the mantles of these bodies. But even for inner solar system iron meteorites, the numbers are lower than 1. There is some amount of iron missing in the cores of these bodies. So the next question is that this number is not equal to the iron by nickel ratio of the bulk. The numbers are slightly lower. So this idea, these planetesimals accrete the silicate condensation line, kind of challenges that. So how do you quantify? Are these numbers important? How much iron is missing in the cores of these bodies? So one can write this simple mass balance equation over here. So the mass of iron in the bulk planetesimal should be equal to mass of iron in the core plus mass of iron in the mantle. But the point over here is there are 2 unknowns in this particular problem. You can't solve this equation. But if you write the same equation for nickel over here, we know that the mass of nickel in the mantle is very low. So you can ignore that number. Then you can divide these equations. This ratio is known from chondrite numbers. It remains consistent across all solar system materials. These numbers we know from iron meteorites, and then you can calculate this number over here. And what we see over here is the FeO in the mantles of the iron meteorite parent bodies. So what you see over here is that the outer solar system iron meteorites, they contain a bunch of FeO, but even the inner solar system iron meteorites, they contain substantial amount of FeO in their mantles. And in some cases, they also start to overlap with the outer solar system iron meteorites. So the first from planetesimals in the inner solar system, they were accreting, they had FeO in their mantles. So basically, if you look at the solar nebula, if you look at the C/O ratio of the nebular gas, so all the iron in this kind of case should have condensed in the form of metallic iron. So you need to start from here and need to increase the oxygen fugacity of the system by almost 4 orders of magnitude. So how do you do that? You need to have an important oxidizing agent which should be present in substantial enough quantities. And that oxidizing agent in the early part of the solar system is water. So if you have to have FeO in the mantles, you must be accreting some water in these planetesimals. And if you do these calculations, and then you can predict the minimum amount of water that must have been present to oxidize the iron that was present in the mantles of these bodies. Again, this is the minimum amount of water that should be present. Most of the water, because it's a free-flowing system, and it's an open system because it's very high porosity and permeability, it's almost like a rubble pile asteroid. Most of the water could have lost without reacting with the rocky material. So the actual amount of water accreted by the early solar system planetesimals could have been substantially higher. So this kind of tells us that the earliest planetesimals in the inner solar system, they were accreting water-bearing materials. So I'm not trying to go into like what current astrophysical models are correct. Did we have one migration of, like, did we have two-step migration of the snow line? Was the water snow line dynamic because you had variations in the mass accretion to the disk, which could have caused large-scale temperature fluctuations in the disk? Or these planetesimals were accreting in outside the water snow line, but still in the inner part of the solar system? We can't resolve these conundrums over here. So the last question is, if the earliest form planetesimals were accreting nitrogen and carbon and water-bearing materials, why are the inner solar system planets and Earth so volatile depleted? So what you see over here is these planetesimals were accreting as rubble pile asteroids. They had very high porosities and permeabilities. So you could have a large-scale open system volatile loss during this early stage heating of these planetesimals because the planetesimals are not centered down. And this is what we see from the chondritic record as well. So if you look at the nitrogen abundances of different class of chondrites, plot them together, you see the nitrogen abundances start to drop off as the temperature increases, and the iron meteorites are the end member in this particular case. So you can have almost 2 orders of loss of nitrogen in these early solar system planetesimals due to this open system loss in these very small planetesimals. And the same story holds for carbon over here. So basically, this tells us that the first form planetesimals in the early solar system, they were accreting nitrogen, carbon, and water. But due to the geophysical evolution of these planetesimals, you would be losing a lot of this early accreted nitrogen, carbon, and water, and eventually resulting in volatile poor planets. So you do not necessarily have the accretion or the building blocks of planets to be almost volatile free. The planetesimals or the building blocks could have accreted volatile bearing materials, but these volatiles were lost during the geophysical evolution of these planetesimals. So basically, I hope that I've convinced you that the processes that are taking place in the early solar system over here are shaped by 26 aluminum decay. And these processes, how important are they for exoplanets? We don't know, because that's a critical parameter we don't understand as well. Did the extrasolar system or the other stellar systems, are you accreting similar amount of 26 aluminum or lower? Because eventually, if you want to form an Earth-like planet, you need to lose the volatile elements. So the 2 key take-home messages from this particular talk, if you remember, are that the earliest planetesimals in the inner solar system, they accreted carbon, nitrogen, and water-bearing materials. And secondly, the volatile inventory of the Earth was shaped by processes during its Earth's entire accretion history, but more importantly, the processes taking place very, very early in the solar system history. Thank you.
Thanks so much for that tour through the early solar system history. I worried for a moment you were going to find not in favor of Tim's model, but luckily the story had a happy ending. Lots of questions. Let's start on the end then.
Hi, Alicia van Koten, Starplan, University of Copenhagen. I was wondering, in your model, you're taking carbon and nitrogen from the organic composition, for a secretion, but why wouldn't you do the same with hydrogen? Because you also have organics containing hydrogen. That could account maybe even for the water observed in your planetesimals early on.
Yeah, I think the thing is because when you could have that, right? But the point is you need to have an oxidizing agent. When we are tracking the role of water through oxidation, so then you have to have water. But the thing is the organics, all the stuff that is present in the organics is in the form of reduced form. So if you disintegrate organics, you still would be reducing stuff because you still need to oxidize the organics somehow. Because you look at the more important components, carbon is still pretty reduced in the organics. So if you have to go from the organics, I'm not talking about ices over here. In the inner part of the solar system, probably they are not CO2 or CO-bearing ices. So it's probably in the form of organics. And the carbon oxidation state in the organics is -4. So you need to oxidize that carbon as well so you need to have even more water than organics to have iron oxidation. Because if the water content is lower than the organic content, you'll still be reducing stuff. So the water content has to be higher. And if you look at chondrites, you see this kind of an evidence.
Great. Other questions? Yes, right at the front. We've got a microphone. Brilliant. And yeah, thanks. If everyone, you could introduce yourselves, institution, that'd be great.
Leonie Janssen from Leiden University. Yeah, thanks for your talk. I was curious because, so you said that the only way to sort of oxidize iron will be by accreting water. And I'm wondering, because also there are quite a lot of silicon condensates that are actually very oxidized. So is there a reason why you could not have oxidizing silicates kind of as solids reacting with the iron to also oxidize the iron?
So are you talking about silicon being oxidized? That's what you said?
Yeah, for example, if you have SiO2 or Mg2SiO4.
So this just depends upon the oxidation potential of these different elements. So basically, if you look at the nebular conditions, the C/O ratio of the solar system. So basically, most of these elements, if you look at magnesium, calcium, aluminum, silicon, they have to exist in the oxidized form under those set of conditions. They're already, because that's controlled by the C/O ratio of the nebular gas. When you're condensing this stuff out from the nebular gas, these things are condensing already in the form of oxides, because this depends on the chemical potential based on the C/O ratio of the nebular gas. But iron is the only major element which can show this variable oxidation state because it's condensing out in the form of metallic iron in the early solar system. But the other things are condensing out in the form of SiO2. But now SiO2 cannot oxidize iron because it just depends on the chemical potentials of these different elements. If it was the other way around, if Si was sitting with FeO, the reaction would have taken place because it depends on the Gibbs free energy of the entire reaction. But the opposite reaction cannot take place because it's not thermodynamically feasible. So you need a thing that it's just based on what has more affinity for electrons at those set of conditions. So water, so these major elements, they do not want to get reduced to oxidize iron. So you cannot do that. But water is one of those things, is a major thing that reaction can take place.
Thank you.
Helen.
Helen Williams, Cambridge. So if I understand you right, you're invoking organic compounds to explain the carbon and nitrogen budget, ices potentially to explain the water budget, but a lot of people use nucleosynthetic anomalies in metals or semi-metals with low half-mass condensation temperatures, so zinc, germanium, to fingerprint different planetary building blocks. Would those kind of elements be completely decoupled then?
Can you be a little bit louder? I have a hearing loss, so can you just...
Sorry.
Yeah.
So what about semi-volatile metals, or so to say elements like zinc and sulfur? What do you think the carriers of those elements would be during accretion?
Yeah, I think it's mostly iron, sulfides. And what you see in iron, me too, as we had another paper I didn't talk about over here, the moderately volatile elemental abundance is almost chondrite-like in these bodies. So they're accreting all these moderately volatile elements, germanium, gallium, copper, almost on the orders of 10 to 30% of Ci chondrite level. So but they are all coming out. But the thing is, right, it just depends. So basically, if you look at Ci chondrites, all of these elements are present in this matrix, in the matrix component. They're not condensing in the form of primordial metal, right? The question now comes in this, like, is this matrix is the primary supplier of these things? Like, how are these condensing? We just don't know. the equilibrium calculations can show us that it could be in the form of metals and sulfides, but it could also be this matrix kind of reservoir.
But then in that case, what you might argue is that people who are using these kinds of volatile metals and using isotope-based isotope systems as tracers for other volatiles like carbon and nitrogen, that potentially they're coming from different components.
Yes, organics. So, okay. I think the water accretion history is distinct from the organic accretion history, which is distinct from the moderately volatile element accretion history. So they're all three different things. But I think when people talk about this problem, they club everything together. Exactly. So when we have to be very careful about this particular problem, because, that's my answer.
Great. I think let's take one more question. Could the next, we might be able to fit two more in, but could the next speaker come on down and get set up so we're good to go once we finish with the questions? Thanks so much. So the next question just over there, Chad.
Oh, okay.
Shardar Bukhari, York University. I think my question would be a follow-up of this discussion. I'm not a geochemist, but there is this very famous plot where we have the relative abundances of almost the entire periodic table relative to, I think, CI chondrite as a function of the condensation temperature.
Yes.
And we use this slope to evaluate the devolatilization trend or things like that. Does your work suggest that we should entirely revisit this kind of reasoning, since the volatility is not really important here?
Yeah.
Because we do accrete very volatile element in the inner solar system, and then it's subsequent processes that would actually explain the volatile content of the planet.
So can you, again, because can you just repeat? I want to answer your question, but I just want to hear it properly.
So, yes. Those devolatilization trend that we usually take from the relative abundances of those elements as a function of condensation temperature, those trends are still meaningful.
Yeah. Sorry, I didn't.
Okay, we can talk maybe.
Okay.
I think the question, it's like, the volatility trend.
Yes.
Yeah, it's a function of condensation temperature.
Yes.
I think what's the significance for your results for the interpretation of that trend?
Okay. So I think basically, okay. Yeah. So basically what I would argue is that the volatile depletion patterns are probably caused by planetesimal collisions that are taking place in the early solar system. So basically the planets are not necessarily made up of first generation planetesimals. So you are also accreting planetesimals which are undergoing processing, and you are creating second and third generation planetesimals. And a fully formed planet is an amalgamation of all these different kind of materials. And that is probably explains the volatile depletion pattern of the Earth. So that would my argument be. So basically you are not accreting the most primordial materials. So you are accreting reprocessed materials as well. So basically think about it, when you have meteorites, the goal in meteorite community is you go from a meteorite and then to try to understand the protoplanetary disk chemistry, but you're assuming that this thing is a first generation planetesimal. But planetesimals before accreting to planets could also have undergone reprocessing. You could have created second and third generation planetesimals. And if a planet is an amalgamation of all these different kind of materials, of unprocessed and processed materials, you would always have a volatile depletion that you would see for those things. Did I answer your question? Okay, thank you.
Cool. I think let's, in the interest of time, leave it there for questions now, and thank Damon again for a really wide-ranging. Right, moving on now, we've got Shasuke Itsumi, who's going to be talking to us about angular momentum conserving extension of smooth particle hydrodynamics to elastic dynamics. Take it away, and I'll be over there waving. Okay, thanks.
Thank you for the introduction. I'm Shusuke Utsumi, second year master course student in Nagoya University, Japan. This is my pleasure to give a talk here, and today I will illustrate a novel scheme for simulating planetesimal collisions that drives the formation of solid planets, rocky balls. Okay. It does not, okay. Okay, first of all, how are rocky planets formed? Previous study revealed that collisions of planetesimals are dominant in this process. They repeat, mergers, and growth, and then solid planets like the Earth are formed. However, the Earth had globally melted in the past, then no information about the formation, about the time of formation is retained. So there is no information. We can't. It is difficult to say something by only investigating on the Earth. However, by the way, remnants in the collisions of planetesimals that did not grow into planets are asteroids. So asteroids are the only entities that record the information of history of planetesimal formation. So by studying the formation of asteroids through collisional phenomena, we can reveal the process of forming solid planets and then the evolution of the evolution of planetary systems. And previous studies have found a lot of asteroids, and they have various shapes, especially the formation mechanism for top-shaped asteroids, like in the right figure, Ryugu, has not sufficiently studied. So we have a promising scenario dominated by angular momentum. First, two planetesimals collide each other, and then since the opposite velocity cancels and emerge into perpendicular direction, ejector curtains like a plane shape object is formed. This process is verified by Sugiura to 2021. And then after that, since the ejector curtain have large angular momentum, they can fragment and reaccumulation, and then maybe become the top shape asteroids. However, this fragmentation and reaccumulation process is not sufficiently studied. So we have to conduct simulations with methods that strictly conserve angular momentum, because angular momentum is dominant in this process. So we should construct simulation. We should invoke simulation that strictly conserve angular momentum. Okay. Then let's see how to simulate such processes. Smooth particle hydrodynamics is a very famous scheme to simulate the behavior of fluids. And to simulate continuous fluid of physical quantities are discretized in space by superparticles. And especially to simulate planetesimal collisions, such as SPAs, including elastic dynamics, that describes the solid bodies are required. Okay, then let's move on to how existing SPAs extended elastic dynamics are. In the left side, I write the elastic dynamics basic equations used in existing models. Mass conservation, momentum conservation, energy conservation, and equation of state, and moreover, equation of deviatoric stress tensor, where sigma alpha beta represents stress tensor, which is composed of pressure and deviatoric stress. The former pressure can be negative for the attraction, and deviatoric stress is only required for elastic dynamics. We don't need this in pure fluid dynamics. And deviatoric stress is not required for fluid dynamics. And you see, this is significantly complicated. Okay, so that's why previous methods have two fatal problems: computational cost and angular momentum conservation. The first one is I rewrite the equation of deviatoric stress here. So you see, this is 5 simultaneous differential equations. And in the right-hand side, expanding the summation results in no less than 20 terms. This is too much. So we can say this equation caused too large computational cost. Okay, and second problem is angular momentum. Existing model interacts by non-central force. So, for example, non-central force includes friction force on sliding block or Lorentz force. Whereas central force is gravity or Coulomb force or F equals minus kx force. For this reason, total angular momentum is not conserved in existing models. So these two problems are fatal in simulation of planetesimal collisions. Okay, so existing models to have two significant problems so that we construct a new formulation, SPS plus F equals minus KX force. We can simulate with central force only, but still can reproduce realistic solid materials. Okay, let me briefly explain the basis of our method. First, we discretize the continuous elastic field with superparticles, and we extend SPS formulation to elastic dynamics, including F equals minus KX force. And then we have several properties. So it is suitable for describing dynamic phenomena, since it is a particle method, and represents the non-diagonal components of the stress tensor only with central force. And it conserves angular momentum strictly. And it significantly reduces computational costs. Here, although we have conducted many test calculations to validate our method, since time is limited, I illustrate 3 examples of test calculations. Tensile testing on solid body, and vibrating an elastic plate, and rotating an aluminum sphere. The first one is solid body tensile testing. In elastic bodies, Poisson's ratio and Young modulus is crucial parameters. It determines the mechanical behavior, mechanical characteristic of material. So we need to reproduce orbital value of 2 parameters. And we measured 2 values. The left upper figure shows Poisson's ratio, and the lower figure shows Young modulus, where horizontal axis is a model parameter. We can set any value of this parameter. So you see Poisson's ratio between 0.25 and 0.5 is achieved. It matches the theoretical range of value of Poisson's ratio. And moreover, in the upper figure, black diamond and pink square shows Poisson's ratio along y-axis and z-axis respectively. So we can, and these 2 values are matching very well. So we can say that Poisson's ratio in 2 directions is the same, and that isotropic materials can be expressed with our model. Okay. And secondary, we vibrate an elastic plate to see our method's finite strain. So I state, this is the result. You see it stably vibrates and reproduce the realistic oscillation of the plate. Okay. The third test calculation is rotating a sphere. We rotate an aluminum sphere to see how our method conserves angular momentum. So we set aluminum sphere in initial conditions like this. So it can stationarily rotate, and we calculated the final angular momentum error. And it found to be very small. So our method is indeed capable of conserving angular momentum. And moreover, I measured the computational time. So it was 7.6 times faster than existing method. Our method is fast. Okay, here is summary. So we extended smooth particle hydrodynamics to elastic dynamics. So it can express orbitally linear isotropic properties, and it achieves significantly lower computational costs. And moreover, it can conserve total angular momentum strictly. That's why we conclude that our method can be used for simulating planetesimal collisions. Thank you.
Questions? Yeah, let's start in the middle.
Hi, Adrian Postman from UC Davis. I have a question. Have you tested like SOD, shock tube things? Have you considered if that shock waves are properly modeled?
The answer is no. But since this our simulation, our methods extend smooth particle hydrodynamics, there is a Godunov type scheme for SPS. We can easily extend our method to that to be capable of capturing shock tubes.
Well, the default SPH form is capable of modeling shocks. Like the normal vanilla SPH models shocks fine. So have you confirmed that you can reproduce that behavior?
I haven't confirmed, but I think we can easily extend it to achieve to capture shock tube.
Okay. And then also, have you been able to model like thermal effects? Can you confirm that like thermal energy is conserved?
Sorry?
Thermal states.
Thermal states. Yes, our methods conserves total energy exactly. So our method can reproduce the thermal behavior of elastic bodies. Yes.
Thank you. Could the next speaker come down and we can change over slides whilst we just take the question on the end of the row there? Thank you.
Just a quick question. Here.
Yes.
So how does your result change with the size or resolution of the size of your superparticle or the resolution?
I don't get the point. Sorry, can you say that again?
Your SPH particles. Okay. How does your result change when you change the size or resolution of your superparticle?
So you mean the resolution, dependence on resolution. I haven't checked. But
what was the resolution that the simulation you showed?
I see. This is a preliminary result, but it seems to be second order accurate in space. Okay. Yes.
Brilliant. Well, let's thank Shizuki again for the talk. Thank you very much. And now we're moving on to Lucy Taylor, who's going to be talking to us about determining observational signatures of post-impact bodies using simulated terrestrial giant impacts. So thanks very much.
Okay. Well, that's really loud. Sorry.
So I will just stay there. Just leave it there. Sure.
Hi, I'm Lucy Taylor. I'm a final year PhD student at the University of Bristol, and today I'm going to be presenting some research on determining whether collisions between rocky worlds or terrestrial giant impacts are observable. It's off to a great start. Sorry. Oh, sorry. Everyone does it, I guess. Okay. So giant impacts are collisions between planet-sized bodies, often considered to be the final stage of planet formation. And you can get giant impacts that are the result of other dynamical instabilities sort of later on in the lifetime of a system, but typically associated with planet formation. As you might imagine, two planets smashing together is an incredibly violent event that's going to release a lot of energy. And there is also strong evidence that giant impacts have, in the distant past, taken place in our own solar system, and kind of bestowed upon it some incredibly recognizable features. But it would be incredibly remiss of us to just say, okay, giant impacts occur at the same frequency, and just like in other solar systems, and just sort of extrapolate that giant impact record to other solar systems. We don't actually know if that is a good thing to do, basically. We want to determine how often these events occur in general in exosystems so that we can understand planet formation models better, because different people have different ideas about whether giant impacts are like essential to planet formation, or if we can kind of get away with other impact-free methods. So how we go about detecting impact processes in another solar system? Well, basically, we're just looking for thermal and/or compositional observations that are not compatible with like a calm, impact-free system. We can look at emission from debris. Obviously, debris doesn't have to be the result of like a significant recent impact. It can just be left over from like a protoplanetary disk. But if we're seeing like significant and varied thermal emission from that debris, then that may be indicative of a recent significant or potentially giant recent impact. Also, we can study the large-scale compositional features of gas in other solar systems, and if they're like evolving on timescales that we can observe changes. That may be indicative of like a vaporized impact ejecta like sweeping through a system. But the one that we're kind of going to focus on here is direct emission from sort of a giant impact event that we've seen like in the act, and it's like very immediate aftermath. Because for both of these slides, I've kind of had this artist impression on the right of a giant impact, but like, what does a giant impact actually look like? And if, more relevant to us, would it show up in observations? So to get an idea of, okay, what do giant impacts look like, we can really only study this by simulating them. We also use SPH, smooth particle hydrodynamics code. It's got a very broad variety of uses. So we start off with like two very calm looking rocky worlds, Earth-like in mass and radius at this a 0 hours snapshot. Those like planets are essentially split up into a load of small particles of mass. And then they collide and evolve. So this is all color-coded by density, and we can see at the end we've ended up with something that is like much larger than we started off with, because this is all like on the same scale. And we can see, although I don't know how clear it is, but there's like a load of really, really low density material here. So we've like vaporized, not just melted, but vaporized rock. And we've got something that's like in a cloud of low density material. So, okay, we've got a representation of a giant impact. How do we calculate how it's going to show up in like thermal emission? So we need to locate the photic surface of this post-impact body, essentially modeling absorptivity of photons passing through this like grid of simulated material. The location when the photons would definitely have been blocked is our photic surface, if you prefer to think of it as emission. Basically, if you look at it and you saw the emission, where does it appear to have been emitted from? This is what we're trying to locate. So, okay, we've got a good representation of a giant impact. We know that we have to find this photic surface, and we have some absorptivity models. So this must be like fairly straightforward to combine, except it isn't. So basically, to accurately model, to accurately locate your photic surface, you need your simulation to have a very, very high resolution. Because if you have a high resolution, more particles involved, then those particles can have smaller masses, so you get like a more accurate overall mass distribution at the end. But we are limited to how much we can increase this resolution due to computational efficiency. We could kind of push to high resolutions by compromising on like the accuracy of other things that we need to capture to model this giant impact simulation. The problem is that we also need those particle densities and thermal properties to accurately find the photic surface. Capturing these values accurately is also computationally very expensive, and we can facilitate it by reducing the particle resolution, except we need a high particle resolution as well. So it's kind of like a catch-22 situation. And also, to find this photic surface, we need to conduct an incredibly complex multi-phase and also multi-material analysis, because vapor and condensate are going to absorb photons in very different ways. And the silicate mantle and iron like core material are going to behave very differently thermodynamically. So again, we require accurate densities and thermal properties. Also, SPH codes do not include material mixing. So we need to sort of like come up with a way of, okay, if we want to look at a point and interpolate some particles that are made of different materials, how do we assess the thermal properties at that point? So basically what we've done is developed a new post-processing pipeline. So we run our simulation at a high resolution, and then we post-process the data so that we can recover and emulate the thermal properties we need that are accurate enough to then find the photic surface. I'm not going to be talking tons about like the actual the gory details or juicy details, depending on if you're like a glass half full, glass half empty kind of person. it's very complicated. If there'll be a paper. If you have questions about specifics, please do come talk to me. Okay, thank you. So we've run our simulation. We've sort of modeled photons passing through this material, and we've come up with this photic surface. And we've color-coded it by the temperature that we record when we go from optically thin to optically thick. And you can see there's kind of this cooler material. That's a material that's been like the absorptivity is controlled by vapor. Condensate actually. And then the green, like hotter material, that is when absorptivity is controlled by vapor. And we can, I guess what I really want to point out here is just how large this object is. This is sort of roughly, oh my God, I broke it. 400 Earth radii across. And if we look at like how this compares to like the Jupiter Galileo moon system, that could kind of, this object could kind of engulf most of that. So it's a pretty big object. So we've kind of come up with a map of temperatures of a photic surface. And again, this was just for terrestrial impact. And we can get an effective temperature, not like of all the material, but of all the material we can see. And because we have like a spatial like map here, we can calculate a luminosity to go with it. This is a very large luminosity. So this object is kind of exhibiting temperatures and luminosities that are similar to that of a star. So we should compare it to stars. So I've got like a Hertzsprung-Russell diagram of stars seen by Gaia with like temperature and on the x-axis, sort of this x-axis, and luminosity on the y-axis. And if we plot our photic surface for this terrestrial giant impact, we see that we're kind of getting objects that are maybe that have the same kind of properties at this stage anyway as M dwarfs. And we've checked this for like a variety of different simulation sort of settings, so smoothing lengths and resolutions if people are familiar, and we kind of get always in the M dwarf region. So this object, while it may only look like this for a short amount of time, we don't know, would definitely be something that is astronomically observable. So yeah, that's pretty much it from me. So current state-of-the-art giant impact simulations can't on their own accurately resolve the properties we need to extract photic surfaces. But we've developed a post-processing pipeline that can simulate giant impact data. That doesn't look like that. I think I've broken all the videos. Anyway, we conclude that giant impacts could potentially be astronomically observable objects, even for terrestrial giant impacts. Rocky worlds are cool. More detail in the paper that has lots of cool stuff like time evolution, which that was meant to be. And also like checking that the pipeline is robust to simulation, like data quality as well. And obviously like the horrible maths for the pipeline. So yeah, that will be published soon because I'm finishing my PhD soon. So if you or someone you know is looking for a postdoc, please let me know. So yeah, thank you very much.
Thanks so much, Lucy. Questions? I'm going to favor the back first, else I'll forget. So Xander, I can see your hand up, and let's move down from the back.
Hi, thanks very much. It's very cool stuff. Xander Byrne, University of Cambridge. Have you looked into whether such an impact could be observable in archival data from, for example, ZTF or Assassin?
So there is already a potential giant impact candidate in Assassin and WISE data. It was kind of like an observed big spike in infrared as seen by, I think, WISE, and it was flagged to be looked at as like the supernova survey. And they saw a big like optical transit as well, like potentially a load of debris passing in front of the star. So they think that there was like a Kenworthy et al. 2023 Nature paper on that. And so that's kind of like, I guess, goes very hand in hand with this. And there may certainly be a lot of archival data that maybe hasn't been identified, because identifying that potential giant impact required like putting different observations from different telescopes together at the right times. But yeah, definitely. Thank you.
Thanks very much.
Great. Could the next speaker come down and start setting up just whilst we continue to get some more questions? Yeah, there's a question just, yes, there, yeah.
Hi, Andrea Zorzi from Stanford University. Thank you for your talk. I was just wondering if the luminosity of the event scales with the kinetic energy of the impact?
Sorry, I didn't hear the last bit. The luminosity of the event scales with.
With the kinetic energy of the impact?
Yes and no. I need to kind of look into that in more detail. We get a slight variation in the luminosities that we record based on our simulations. So I think we're expecting it to. We've kind of done some like very preliminary back of envelope calculations that would suggest that, but we need to do a lot more verification with a lot more like different impact scenarios as well. But we're kind of expecting that to be the case.
Great, thank you. I think for the sake of time, we're going to have to move on. Thanks so much, everyone, for your questions. And thanks, Luca, again. Next up, we have Elisheva van Kooten talking to us about revisiting Earth's origins, linking terrestrial accretion to outer disk dynamics. And that'll be the last talk of the session before we break for coffee. So thanks very much.
Thank you. So yeah, I'll be talking about trying to link the dynamics of the outer protoplanetary disk to the inner disk. So learning more about Earth's accretion, taking the entire protoplanetary disk into account. So in preparation of this talk, I've been trying to think a bit about what we know actually about Earth's accretion, trying to read different publications, and it seems we cannot find a lot of consensus so far on how we think Earth accreted. So I try to be a bit conservative here and just state from the point of view of this talk, Earth started with some chemically reduced materials and then moved on to accrete more oxidized materials. And we think, conservatively again, that the relative contribution of the outer disk must be somewhere between 4 and 40 weight% of water-rich outer disk material. But the mechanism of this trend remains heavily debated. And I think if you watch Paulo's talk tomorrow, it will be even more conservative. We can go to 0% contribution, right? All right, so just starting from that, we can look at Earth's accretion from different perspectives. So chemical, isotopic, and astrophysical perspective. And somebody asked a question about the moderately volatile element depletion trend of the Earth. So this is just one example showing how Earth is moderately volatile element depleted. So the more volatile you get for your element, the more depleted in Earth. What people haven't shown so far is that some people think that at the end of this volatile depletion trend, so for the most volatile elements, we no longer dip down like this, but we stay a bit more flat. And people think that this is due to a contribution of 10 to 15 weight% of CI-like material. So this is material similar to samples returned from Bennu and Ryugu asteroids. These are water-rich asteroids with a near solar composition. Then from an isotopical perspective, I'm showing here an example in zinc versus chrome isotope space, where you can see these dots over here representing inner disk materials, the blue dots outer disk materials, and here these CI chondrites. And you can see Earth here in green. And you can see from these different mixing lines that depending on which end member you take from the inner disk, we can imagine we have either 4 weight% of outer disk material up to 40 weight%. And maybe the truth lies somewhere in the middle here. Oh, I'm doing the wrong thing. Yeah. So then from an astrophysical perspective, we know that the disk has some kind of thermal gradient. So you can get colder the more you move outwards. We have these different ice lines that can move further out, maybe during outburst, but they can also move back in again. So we have evaporation and recondensation processes. And then we also have thermal processing of material in the planetary envelopes as well. So we have a lot of things going on in the terrestrial planet region in terms of what kind of processes are happening in the disk. Right. So I think in summary, we can say to some degree, the terrestrial planet region is receiving water-rich dust and pebbles. Material is, again, to some degree, thermally processed upon accretion to these rocky planets. So then how does the outer disk link back to the inner disk? And when I talk about the inner disk, I'm talking basically about the terrestrial planet region. When I'm talking about the outer disk, anything beyond the asteroid belt. And you can see from this image, if we want to take materials that are left over after planet formation from the outer disk, we're looking a lot at comets. And we don't know the composition of comets. So an interesting question to define the outer disk evolution would be, what do comets look like chemically and isotopically? Since it's very difficult to go to a comet and grab some material from there, we have to depend on our meteorite collection. And we've actually found a couple of years back these very interesting, what we call xenolithic dark clasts. So you can see an example up here of these clasts. These are chemically solar-like materials, very fine-grained. They look optically dark. So they have the same chemical composition as CI chondrites, but isotopically and mineralogical, they look quite different from them. So they have a few distinctive features that makes us think that these are the type of materials that represent the outermost disk best. They represent the cometary accretion region. So for example, they have some very 6 pore compositions. They resemble in a lot of different features, cometary interplanetary dust particles. They have these specific organic structures that look like these interplanetary dust particles. And they're particularly 50 nitrogen and deuterium rich. So they have some features that makes us think these represent the composition of the outermost disk. So we were able to measure the nucleosynthetic isotope composition of these materials. And we found that we can divide the solar system into 3 main isotopic end members. So I'm not going to talk much about the inner disk isotopic end members, but just to show you that we think the outer disk is a mixture of 2 main end members, which are these cometary dark clasts, this cometary material up here, and the CI chondrites, so Bennu and Ryugu type asteroids that I just talked about. So you can see here this mixing line, and all these blue dots are the carbonaceous chondrites, so these water-rich asteroids. And since we don't have a lot of points on this line, the next thing that we did is to take a lot more samples that we call ungrouped chondrites, so they're not easily classified into any scheme, and measure the silicon, iron, and magnesium isotope compositions of these materials. So these are the main rock-forming elements that we have. And you can see for those elements that we see here in silicon versus iron, here in silicon versus magnesium space, that all these materials represent mixtures between this cometary material up here and the CI chondrites up there. And this is then also data that has not been published yet, so please don't take pictures. You can see that Bennu and Ryugu asteroids also just extend a bit from this CI end member down here. All right. So then, if we notice that we have these 2 end members, where do we place the accretionary reservoirs of these materials? So which materials would link back closest to the inner disk? Traditionally, we've been measuring chromium isotopes of different solar system materials, and people thought of this gradient where the more enriched you are in 54 chrome, the more outwards in the disk you are. And this is why CI chondrites traditionally have been seen as outermost disk materials, most closely resembling comets. The problem with that model for us is that when we try to plot the chrome isotope data of all these outer disk materials into silicon versus iron space, so with these 2 main end members, you see there's absolutely no correlation between chrome isotopes and the rock-forming elements. So how can we explain that? Well, we explain that by looking at this correlation that chrome also has with oxygen isotope signatures. And their oxygen isotope signatures don't only represent the rocky component of these materials, but they also represent the ice component. And we see this positive correlation down here. Now, the other thing we've observed in terms of oxygen and chrome isotopes is that they also correlate with the chrome versus matrix ratio of different carbonaceous chondrites. So that means that the higher the chondral matrix ratio, the more thermally processed material you have. And if you go to this side of the trend where you interact with the cometary material, this represents the most ice-rich, less thermally processed component, right? So in that sense, you can say that if you deplete 17 oxygen, if you go into that direction, that material is more thermally processed. It has seen thermal processing of its ice component. So in that sense, you could also say that CI chondrites themselves have seen reprocessing of this ice component. All right. So now knowing this, we can take into account several key features of CI chondrites. So first of all, they contain a high abundance, but also thermally processed water ice. That means they must form at a location where you have sublimation and recondensation of water ice. The second important feature about CI chondrites is that they contain a very, very low fraction of refractory inclusion, so CAIs and chondrules. And this means that in contrast to other carbonaceous chondrites, they must have formed somewhere where you can filter out these components. And then the last thing is that we have a high prevalence of these CI-like bodies in the asteroid belt. So going to Bennu and Ryugu, we know that these kind of bodies are very important or very present in the asteroid belt. And this must mean that we should have an efficient planetesimal formation scenario for these bodies. So all in all, I think a key location for these CI chondrites is at the water ice line. So right here. And that means that if you would have a radial barrier, for example, Jupiter here, that would filter out these refractory components, like I said before, the inner disk has both these non-carbonaceous asteroids, but it also accretes a lot of CI chondrites at the ice line. And the ice line is something that is present in the inner disk in the terrestrial formation region. So these are the materials that can also contribute to Earth's local feeding zones, whereas the other carbonaceous chondrites and comets contribute very little to Earth secretion, maybe only at the very last stage, like the very last, less than 1% of the mass. All right, so then of course the question is, what happens to these materials when they accrete to Earth? Do they accrete to Earth when Earth is already within the ice line? Or do they accrete to Earth when they move past the ice line and get thermally processed here? If you want to learn more about that, please come to my PhD student Cyprien Camplong's poster. He is looking at the thermal processing of CI-like materials when they pass through the inner disk. Very last, I just want to mention, I'm from Starplan, University of Copenhagen. We have this very nice PhD summer school called Dust to DNA. If you want to learn more about it, go to dusttodna.dk and sign up. Thank you.
Thanks very much. Questions? Yeah. Sorry, just in the middle there.
Hi, Hannah Sanderson at University of Oslo. Thanks for the great talk. So in your cartoon you put at the end, you're suggesting that the CIs have actually formed closest to the NC reservoir and other CCs have formed further away. But as you kind of also illustrated in the cartoon, somehow you're proposing that the CAIs kind of are skipping that region and not ending up in the CIs. Do you have a hypothesis as to how that happens?
What is skipping?
The CAIs and the refractory components are not ending up in the middle region, they're only at each end of the disk.
Yeah, so one of the things I haven't talked about is what fraction of the inner disk in the end ends up in the outer disk, right? We know we have CAIs in the outer disk in the carbonaceous chondrites and less so in the inner disk. So there must be some transport of these materials outwards. At the same time, we see very limited evidence that the inner disk is present in the outer disk. So we have some chondrules where we see this, mostly in these CV type of chondrites, but we don't really see that in the other carbonaceous chondrite groups. So what we envision is that we have some kind of mass transport outwards very early on that can take some CAIs, possibly some chondrules, but not much else. And the way we think of that is through disk winds, for example.
And the CIs then form after that, so they don't get that component?
Well, they could form before that, but if you form a barrier very early on, you're just not putting that material through that barrier, so you cannot accrete it at that point at the ice line. Thanks.
Yeah, let's take a question from Melissa here as well. Yeah.
Hi, Melissa McClure, London Observatory. Great talk. I'm just a little perplexed in this figure. Why do you have the snow line interior to Jupiter's orbit?
This is based on several astrophysical models. You will move your water ice line inward at some point, right? You can start out at maybe 5 AU, but at some point when the disk is cooling, you're moving inward. And
so then I guess my rephrased question is, what time are you envisioning this figure applying to?
Well, this is of course a very static image of, so maybe 1-2 million years after T0, so after CAI formation. Okay. I think it's pretty common to say, pretty general to say that the water ice line was already at 1 AU within 1 million or 2 million years after T0.
Yeah, it's just that I was seeing the CAIs being transported and interpreting this to be much earlier than that.
Yeah, sorry. Yeah.
Out, but
no, we envisioned that earlier than the position of the water ice line as it is drawn, yeah.
Great. Any final questions? Yeah, let's take the last question just in the middle. I think the microphone's on the side.
I'm Judy Wong from University of Bristol. And wonder, based on this model, do you think CI may contribute to like higher proportion than we thought for the Earth formation, and that might be the oxidation agent, like oxidizing agent bringing the water to the early form contents?
Yeah, so like I said, I don't know if this is going to be 4% or 40% of the mass. But I think if there's any water-rich material that's been supplied by the outer disk, it doesn't necessarily have to be like what we traditionally think of as outer disk material. It can be very local. It's just right beyond the ice line.
Great.
Thank you.
Thank you. So let's thank our speaker again. Thank you so much. So before everyone heads off, we're going to have half an hour for coffee, or just under, but back in here at 3:30, where we'll reconvene and then distribute ourselves out from here for the breakout sessions. And thank you everyone for your fantastic questions and all the speakers in the session.